Hello there, and welcome to Life Beyond Seen, where we take the ideas that tend to drift around in the back of your mind and bring them into a quiet place where you can explore them without hurry. Tonight we're heading somewhere very different from the usual cosmic landscapes or the ticking puzzles of physics. We're going downward, deeper than sunlight can reach, deeper than most technology can function, deeper than anything built by humans can last for long. We're heading toward the region often called Horizon Deep. It's one of the most remote and inhospitable places on Earth, a part of the ocean where pressure becomes a force that doesn't care about intention or ambition, where darkness is not just the absence of light but the default condition, and where reaching the bottom isn't just difficult but almost completely beyond what our bodies and machines are capable of. Before we step into that slow descent together, I'd like to know something simple. Where are you listening from tonight, and what time is it where you are right now? It feels fitting to ask because, while we'll be talking about a place that barely changes at all, we're each meeting here from different moments of the day. Maybe it's late for you, maybe it's early. Maybe you're listening as a way to wind down, or maybe you're here because your mind wants something steady to focus on. Whatever the reason, I'm glad you've joined for this quiet look into a place that most people will never see. And if you find this slow dive soothing or interesting, or if it gives your mind a bit of room to breathe, I'd be grateful if you tapped the like button or subscribed. It helps this small corner of calm reach others who might need it too. There's something strangely comforting about focusing on the deep ocean at night. While everything around you might feel fast or noisy, Horizon Deep remains steady. Nothing rushes down there. Nothing hurries. The weight of the entire ocean makes sure of that. As we begin this exploration, try to let your thoughts slow down with the images that form in your mind. We won't be descending quickly. We're just setting the stage for where we're going, easing into the reasons why this part of the ocean remains one of the least explored regions on the planet. Even with all our technology, all our satellites, all our robotics, all our curiosity, there are limits to what we can manage. Those limits become incredibly clear when you try to understand the bottom of the ocean. Most of us spend our entire lives on the surface without realizing how thin that surface truly is. A few kilometers below it, human equipment begins to fail, and a few more beyond that, the environment becomes more extreme than anything found anywhere else on Earth. There are places in space that are easier to reach than the bottom of certain ocean trenches. That idea alone slows the mind for a moment because we tend to picture space as the frontier humans haven't conquered. But the truth is we've seen more of our surrounding solar system than we've seen of our own planet's deepest points. When people hear the phrase Horizon Deep, they often imagine a coastline or a distant horizon meeting water. But the name refers to a location in the Tonga Trench, one of the deepest known points of the ocean. It's a place that is almost impossible to visualize accurately because there's no familiar frame of reference. Most mountains on land don't come close to the height of the ocean's deepest trenches in reverse. If you placed Mount Everest into many of these trenches, it would still be completely submerged. That's the scale we're dealing with. And as we settle into describing it, it becomes clear that exploring it isn't just a matter of going down and looking around. The forces at play are so intense that any attempt to reach the bottom requires planning at a level most people never consider. There's no margin for error, no backup plan if something goes wrong, and no easy way to retrieve anything that breaks down. Even the act of sending a camera down isn't simple, because the slightest flaw in its structure can cause it to collapse long before reaching the deepest layers. If you try imagining yourself descending slowly from the surface, you begin to understand why Horizon Deep remains so mysterious. At first, the water is familiar. It's illuminated by sunlight. You can see a sense of distance. Fish move around in ways that feel recognizable. But the deeper you go, the more the colors begin to change. Reds disappear first because red light is absorbed quickly. Oranges vanish. Yellows fade. Greens go next. Eventually, everything starts turning into muted blues, and then darker tones until even those disappear. The world becomes a place where only faint traces of bioluminescence appear, and then only if a creature creates them. Past a certain depth, sunlight is irrelevant. The environment is built on pressure more than light. Every 10 meters you descend adds another atmosphere of pressure. At horizon deep, the pressure reaches levels so extreme that almost nothing made for the surface can survive for long. Submersibles have to be designed with materials that won't collapse inward, and even then they can only stay down for limited periods. When explorers talk about how fragile these vessels are, they're not exaggerating. Even a tiny imperfection can lead to catastrophic failure because the ocean doesn't negotiate with structural weakness. It simply takes advantage of it. Part of what makes Horizon Deep so difficult to explore is that the pressures aren't just high. They're constant, unrelenting, and distributed in every direction. It's not like standing under heavy weight. It's like being surrounded by an invisible force pushing evenly across every surface. If you've ever held a heavy object and felt how tiring it becomes, imagine that weight applied continuously from all sides without any break. That's the reality for anything trying to go that low. For humans, that environment is completely incompatible with life. Our bodies aren't designed to withstand that kind of pressure. The air pockets inside us would collapse instantly. Soft tissues wouldn't maintain their structure. Even bones would struggle. And unlike travelling to high altitudes where pressure decreases gradually and the body can adapt to some degree, there is no adaptation available that makes Horizon Deep survivable. Evolution has never required humans to develop mechanisms for surviving those depths because we've never lived anywhere near them. So the idea of going there physically is off the table right away. Only machines can go, and even those machines are pushed to their limits. When people think about exploration, they often assume it's a matter of courage or effort. But Horizon Deep is a reminder that some obstacles are mechanical, physical, and absolute. No amount of determination changes the fact that materials behave differently under extreme pressure. Metals that seem rigid at the surface can deform slowly under the weight of the water. Electronics designed to remain stable can malfunction. Batteries can fail. Even cables used to send instruments down can stretch or snap. Everything has to be re-engineered for an environment that is unforgiving from the moment you enter it. There's no halfway point where conditions settle. The pressure keeps increasing as you go down, and the challenges increase with it. Another obstacle comes from communication. In space exploration, signals can be sent across millions of kilometers. They take time to travel, but they do reach their destination. Underwater, radio waves don't travel the same way. Sound does, but it moves differently depending on temperature, salinity, and depth. At Horizon Deep, communication becomes slow and difficult. The simplest tasks are delayed. It's like trying to talk through walls made of water. And because signals can't be transmitted efficiently, remote-operated vehicles become harder to control. Sometimes they move autonomously, relying on programming rather than instructions. That means any unexpected change in the terrain or any malfunction can't be corrected quickly. The deeper you go, the more isolated the equipment becomes from the people operating it. The terrain itself also complicates things. Horizon Deep isn't a smooth basin. It's a rugged environment shaped by tectonic forces. The seafloor can shift. Landslides can occur. The bottom isn't flat. It contains ridges, slopes, and areas where sediment moves unpredictably. The deeper you go, the more those features matter because maneuvering a submersible becomes dangerous. Even a small miscalculation can trap the machine or damage it beyond retrieval. Scientists often compare it to exploring another planet, but with far more risk and less visibility. And while satellites can map the ocean surface with incredible accuracy, they can't see the trenches. Sonar helps, but even sonar can struggle to measure a place so deep and so dynamic. Life down there presents another difficulty, not because it threatens explorers, but because it's incredibly delicate. Many deep-sea organisms are adapted to survive only in those conditions. Bringing them to the surface can harm them instantly because their bodies can't adjust to lower pressures. Even retrieving samples requires special equipment designed to maintain the pressure around the organisms, but much of what lives in Horizon Deep hasn't been seen up close, and some of it hasn't been observed at all. We know it exists because of indirect evidence. That means there's an entire ecosystem in a place we can barely reach and can't observe for long without disturbing it. To study it properly, we would need technology that can stay down there for extended periods without failing. And while researchers are working toward that, the ocean keeps presenting new complications. Another issue is cost. Building machines capable of reaching horizon deep is extremely expensive. Maintaining them is expensive. Deploying them is expensive. Recovering them is expensive. Expeditions require ships, crews, specialists, technicians, and time. And even with all of that, the results are often uncertain. An expedition can spend millions and return with a malfunctioning camera or a damaged robotic arm. Funding becomes difficult because deep-sea research doesn't generate immediate financial returns. It's important scientifically, but not profitable, so progress is slow. Years pass between missions. Technology advances, but not fast enough to transform the environment into something more accessible. Even when everything goes right, exploration time at those depths is limited. Machines can't stay down indefinitely. Batteries drain. Lights consume power. Inserts weaken. The descent and ascent alone take hours. By the time the vehicle reaches the bottom, its operational window might be small. It gathers as much data as it can, but it always feels incomplete. Scientists return to the surface wishing they had more time. That's one of the reasons Horizon Deep remains unknown. We visit it briefly and then leave. Most of the time it remains undisturbed and unseen. There's also the simple fact that we haven't built enough machines to explore it thoroughly. Most deep-sea submersibles only reach the regions above the deepest trenches. Only a few have ever reached the very bottom, and even those journeys were brief. The ocean is vast and the trenches are narrow, deep, and difficult to locate precisely. Even if we wanted to map the entire area, it would take countless missions. And because technology evolves so slowly in this field, each expedition adds only a small amount of new information. All of this leads to a strange realization. Horizon Deep isn't uncharted because we lack interest. It's uncharted because it defies easy access in almost every way. The technology required to explore it safely and effectively pushes the limits of what humans can construct. The environment destroys equipment if anything is even slightly flawed. The time it takes to reach the bottom shortens the amount of work that can be done. The terrain is unpredictable. Communication is slow. The cost is high. The risk is constant. And yet despite all of that, the idea of exploring Horizon Deep keeps drawing people back because there's something compelling about understanding one of the last places on Earth where mystery still outweighs knowledge. As we continue this slow descent in our discussion, we'll begin moving from the surface-level details into the more complex reasons why exploration remains beyond our full reach. The deeper we go into the explanations, the clearer it becomes that exploring Horizon Deep isn't just a technical challenge. It's a reminder of the boundaries that exist in nature, boundaries that push back against our curiosity. And while curiosity drives us to explore, the deep ocean forces us to acknowledge that some environments remain out of reach for reasons that aren't emotional or philosophical, but simply physical. Even so, the effort to understand Horizon Deep continues because each new piece of information reshapes the picture. Every measurement, every sample, every brief glimpse, they all add to a growing understanding even if the pace is slow. We'll keep following this path without rushing. There's still much to explain about how the deep ocean functions, what life exists there, how physics behaves at those depths, and why certain limitations can't be overcome even with advanced technology. This is just the beginning of the descent, and the layers ahead will reveal even more about why Horizon Deep remains a frontier that resists complete exploration. When you start thinking about the deep ocean, it's easy to picture a simple idea of water getting darker as you go down, but Horizon Deep forces you to reconsider almost every assumption you've ever had about what the ocean truly is. Most of us grow up imagining the sea as something vibrant, colourful, and full of movement at every level. What's strange is that almost all the images we've seen, whether in documentaries or on screensavers, or in the rare moments when we visit an aquarium, come from a very thin slice of the ocean. That thin slice doesn't even begin to represent the environment we're talking about. Once you move beyond the familiar layer where sunlight gives shape to everything, the world below becomes unrecognizable, not in a dramatic or mystical sense, but in a very practical way. The rules that govern life near the surface begin to break apart, and the environment becomes increasingly dominated by pressure, cold, and a level of stillness that feels more like a pause than a landscape. It's a strange contrast. The surface of the ocean is always changing. Waves move, winds shift, storms form, and currents carry heat across whole continents. But far below all that activity is a part of the planet where almost nothing moves quickly. There's a sense of suspended motion, not because time behaves differently, but because the conditions don't allow for rapid change. It's not emptiness, it's not silence. It's more like the ocean stops rushing and settles into a state where everything has to be slow. That's what people mean when they describe the deep trenches as places where the ocean holds its breath. There's no drama in that idea. It's a simple description of an environment shaped by the limits of physics, not by emotion. If you imagine yourself drifting down slowly from the upper layers, you would notice the shift long before you reached anything close to horizon deep. At the start, the water moves around you in familiar ways. Schools of fish dart between beams of filtered sunlight. Colours still hold their natural brightness. But as the descent continues, the world begins to flatten. Reds fade until they look brown, then grey, then vanish entirely. Orange disappears next. Yellows weaken. Greens begin to dissolve into the surrounding water. By the time only shades of blue remain, you're already entering a region most ocean life never visits unless it's migrating. At this point, very little visual detail remains, and what you see begins to depend more on artificial lights than on the environment itself. Then, as you continue downward and the last traces of blue fall away, the surroundings settle into the long stretch of darkness that defines most of Earth's oceans. It's not a dramatic transition. There's no moment where the light suddenly goes out. The shift is gradual, like dimming a lamp slowly enough that you only realise the room is dark after it's already happened. Some people imagine the darkness as unsettling, but down here it's simply the norm. There's no sense of being watched, no sense of danger, no sense of suspense. It's just the natural result of travelling further than sunlight can reach. Even in this darkness, the ocean isn't empty. This is the region where bioluminescence appears for the first time in any meaningful quantity. It's easy to think of bioluminescence as a rare or magical phenomenon, but in truth, it's incredibly common once you reach these depths. Many creatures have evolved to produce light, not because they want to be beautiful or dramatic, but because light becomes a tool. Some use it to confuse predators, some use it to lure prey, some use it to signal possible mates. Others use it to mimic the faint scattered light from above so they can hide from anything looking up at them. But even with all those glowing creatures, the light they produce only travels short distances. The darkness remains dominant, almost like a backdrop that makes their small signals more noticeable. It might seem like these organisms would be the main focus of anyone exploring Horizon Deep, and in many ways, they are one of the few familiar features researchers encounter on the way down. But the further you go, the fewer of them you see. Bioluminescence begins to fade again. Life becomes sparse, shapes become harder to detect. Eventually, only the submersible's own lights reveal anything at all. What those lights show is a place that barely changes, not because nothing happens there, but because everything happens at a much slower rate than on the surface. Sediment falls from above and settles quietly on the seabed. Small currents shift particles from one spot to another. Every movement is gradual, and the environment feels like it's waiting for something. Not for dramatic events, but for the next small shift in pressure or the next slow deposit of material. One of the most misunderstood parts of Horizon Deep is the sense that it's some remote world cut off entirely from the rest of the planet. In reality, The water above is constantly sending down traces of organic material. Fish that die near the surface eventually sink. Particles from plants and microorganisms drop continuously like snow. Tiny fragments of shells and bones drift downward. These things become food for whatever manages to survive in the trenches. But even with that steady supply, life here doesn't resemble anything we see in shallower waters. The organisms that live near horizon deep are adapted to pressures that would crush almost anything else. Their bodies are shaped by necessity, not aesthetics. Many lack rigid structures because rigidity doesn't help at these depths. Fluids behave differently under pressure, and living things have to adapt or they simply cannot exist. As you start thinking about what it would mean to observe all of this up close, another problem becomes clear. Human senses don't translate well here. Our eyes rely on light. Our ears rely on air. Our sense of balance relies on gravity and the movement of our inner ear. In horizon deep, light doesn't exist naturally. Sound travels differently, and gravity interacts with pressure in ways that change the way things feel. If a human could somehow survive the pressure, which we can't, the environment still wouldn't make sense to us in any intuitive way. Our understanding of motion, space, and even distance would feel distorted because our bodies weren't built for water at this density. That mismatch between our biology and the deep ocean underscores why exploration becomes a machine's job, not a human one. But machines also face sensory challenges. Cameras struggle in low light. Sonar map shapes imperfectly. Instruments must be reinforced, and sensors often fail because extreme pressure can interfere with their ability to function consistently. Even capturing a simple image becomes a complicated challenge at the bottom of the ocean. The lights needed to illuminate the environment can frighten wildlife or alter the behavior of organisms that normally live in complete darkness. Cameras have to be shielded carefully. Every choice affects the data collected. Once you reach the depths close to horizon deep, the water behaves differently in ways most people never consider. Temperature drops to near freezing, but not quite. The water becomes incredibly dense. Sound travels quickly but unpredictably, bouncing off surfaces in ways that make navigation harder. Everything that seems straightforward at shallow depths becomes questionable here. Even the concept of bottom becomes complicated because sediment can shift, and slight tremors can reshape sections of the trench floor without anyone noticing. The terrain is constantly subject to the movement of tectonic plates. Unlike a typical landscape, it can change without warning and without any surface sign that something happened. If you imagine the ocean holding its breath, that comparison comes not from a dramatic impression, but from the peculiar stillness that defines these regions. The pressure prevents rapid motion. The darkness prevents visual complexity. The temperature prevents many biological processes from happening quickly. Everything remains in a kind of long, slow pause. Scientists sometimes compare the deep trenches to time capsules because changes occur so gradually that disturbances can remain visible for years. Tracks left by a submersible might linger on the seabed far longer than footprints last on the surface. Sediment doesn't shift quickly. Nothing erases the marks right away. What surprises many people is that this stillness isn't lifeless. There are organisms that thrive in these conditions by being incredibly efficient. They consume very little energy, they move when they need to, they interact with the environment in small, deliberate ways. Life continues here, but on timelines that make human activity seem frantic by comparison. Studying these organisms is difficult because retrieving them usually changes them. The sudden drop in pressure during ascent can damage tissues or destroy delicate structures. That means scientists must invent new methods, pressure-retaining containers, and specialized equipment just to bring samples up without harming them. Even then, the results can be unpredictable. The deeper you think about this environment, the more you realize that horizon deep isn't resisting exploration out of mystery or defiance. It's simply a part of the world shaped by conditions we aren't built for. The ocean at these depths behaves according to rules that don't make room for fragile structures or biological bodies like ours. Pressure sets the boundaries, and everything else adjusts around it. The ocean holds its breath not in a poetic way, but because motion and change here are limited by the weight above, the temperature around, and the lack of energy sources that drive faster processes elsewhere. And as we continue moving deeper into the explanations ahead, each layer reveals something more about the limitations that prevent full exploration. The environment is shaped by physics, by geology, by chemistry, and by biological processes that have adapted over millions of years. These things create boundaries that are real and measurable. Understanding them brings us closer to understanding why the trench remains one of the least explored parts of Earth, even though we've reached it a few times. The descent continues, moving steadily into the next layer of reasons why Horizon Deep remains so far beyond our reach, even with the best technology we've built so far. When people try to imagine what exists below the last reach of sunlight, they often picture pitch-black emptiness. But that idea doesn't really capture what exists there. It's not that the environment is empty, it's that the way we perceive the world doesn't function at all in these conditions. The senses we rely on in daily life are built around light and air and sound moving through open spaces. Once you leave those conditions behind, your expectations stop matching reality. Most of the ocean is a world where light provides no structure, and without light, memory, as we understand it, becomes difficult to form because the normal cues that allow the brain to build a timeline simply aren't present. This isn't a matter of the deep ocean playing tricks on perception. It's a matter of the environment removing the familiar markers we depend on without realizing it. If you try to imagine drifting just a little deeper than where sunlight fades, the environment changes in ways that affect every living thing. Light isn't just a visual input, it's also a signal for behavior. Plants use it to trigger photosynthesis. Animals use it to regulate sleep, navigate, find food, and avoid predators. Once light disappears, none of that applies. Instead, organisms have to rely on signals that don't behave in predictable patterns. Sound becomes more important. Chemical trails matter. Movements of water carry information. But even these cues behave differently in the deep. Sound can travel long distances, yet it's difficult to use precisely because the temperature layers distort it. Chemical cues disperse slowly. Water movement becomes limited. Everything becomes faint, slow, and often ambiguous. If we lived in this kind of environment, our memory would feel different because memory relies heavily on context. Without light, context blur. Without clear distinctions between one moment and the next, the brain wouldn't form memory the way it usually does. That's one reason why the deep ocean, especially near Horizon Deep, feels so foreign. It's not only distant in a physical sense, it's distant in a cognitive sense. The things we use to make sense of our surroundings simply don't exist here. As you imagine sinking further, the last traces of light vanish entirely. What remains is not dramatic darkness, but a kind of permanent night with no contrast. The world here does not change in bright flashes. There are no beams of sunlight. There is no such thing as a horizon. The sea floor, if visible at all, appears as a faint patch illuminated by artificial lights. Without those lights, even the idea of seeing loses meaning. Down here, if a creature wants to sense the world, it has to evolve different tools. Some develop organs that detect tiny shifts in pressure. Others build sensitive chemical receptors. Some use electrical fields. Many use faint glows of bioluminescence to communicate or lure prey, but even these signals are usually brief and functional. Nothing here uses light as decoration. Nothing uses light for display. Light becomes a resource used carefully because energy is scarce in this part of the ocean. We often think of the deep sea as a mysterious place, but the mystery doesn't come from secrecy. It comes from how different the environment is from anything on the surface. Even the simplest movements become challenging. An animal that wants to find food has to expend energy, but there's almost no guarantee that energy will be replenished. That creates a pattern of life defined by extreme caution. Predators don't chase prey often. Prey don't flee in long bursts. Most behaviour is slow, controlled and efficient. There's no waste allowed. The result is a world where nothing seems frantic. Nothing moves in quick bursts unless absolutely necessary. It's not a world built around urgency. It's a world built around conservation. In this setting, the idea of memory becomes more complex. Most deep-sea organisms don't rely on memory in the ways humans do. Their survival depends less on experiences from the past and more on immediate sensory information. They don't need to remember landscapes because landscapes barely change. They don't need to recall the position of predators because predators don't patrol large territories. They don't need to memorize food locations because food doesn't cluster the way it does in shallow water. Instead, their behaviors are deeply ingrained through evolution, rather than learned through repetition. The deep ocean isn't the kind of environment that rewards experimentation. Instead, it rewards consistency. If humans were somehow able to witness life in these depths without distorting it through artificial lights or noise, we would see an environment that feels almost suspended. Things move, but slowly. Creatures survive, but carefully. The world isn't frozen, it's simply paced differently. Think of it as a place where time doesn't accelerate or slow down, but where everything happens within a narrow margin of energy use. Even the act of reproduction happens slowly. Some species lay eggs that take months or years to develop. Some grow at a rate that would seem impossibly slow to surface dwellers. Many produce very few offspring because large reproductive events are unsustainable in an environment with so little food. If you shift your attention from the creatures living here to the water itself, you find something equally unusual. The physical properties of the water create conditions unlike anything at the surface. The temperature remains near freezing, yet the water does not turn to ice because the pressure increases its density and changes its freezing point. This dense water moves slowly across the seafloor. Even currents that look insignificant by surface standards are meaningful here because a small shift in water can carry nutrients or oxygen. The lack of strong currents means that the environment becomes stratified. Different pockets of water can maintain slightly different chemical compositions. Some areas have higher oxygen, some have more nutrients, some have fewer. Even small shifts can influence which organisms survive in a particular region. When scientists try to study this world, they have to rely on instruments that operate in conditions completely foreign to their intended design. Light is useless, so high-powered lamps have to be used, and those lamps change the behavior of the organisms being observed. Sound travels differently, so sonar signals can bounce unpredictably. Sediment becomes a challenge because the lights and thrusters from submersibles can stir it up, clouding the view for long periods. Even taking samples becomes a delicate process. Most sampling containers are built for surface work, not for deep-sea conditions. When they open or close, they can disturb the water around them, change the temperature inside, or break fragile organisms. Many people imagine that deep-sea exploration simply requires sturdier machines. But that assumption overlooks how the environment practically erases the usual tools of research. Cameras don't work the same way. Microphones don't work the same way. Sampling equipment becomes unreliable. Navigation becomes challenging because GPS signals don't reach underwater. Everything that feels straightforward at shallow depth starts to break down as you enter horizon-deep surrounding regions. Even time measurement can become complicated because pressure affects electronics. Instruments have to be tested repeatedly, and even then, failure rates are high. Because of all these limitations, most of what we know about deep-sea life at these depths comes from momentary observations. A submersible captures a quick image or a short video. A remotely operated vehicle collects a sample that may or may not survive the ascent. Autonomous systems gather data in snapshots rather than continuous streams. In other words, researchers are creating a puzzle with the majority of the pieces missing, and many of the pieces they do find are distorted simply because retrieving them alters their original state. That makes building a complete picture incredibly difficult. Even the idea of a stable map becomes questionable here. The seafloor near horizon deep can shift due to tectonic activity. Earthquakes, even small ones, can reshape the sediment. Landslides can occur along the slope of the trench, chasms can open or close, ridges can rise or collapse. None of this happens quickly in human terms, but it does happen regularly enough that maps can become inaccurate between expeditions. This constant slow change means that even if explorers manage to reach the same depth multiple times, they might not encounter the same landmarks. It's like trying to map a desert where sand dunes move, but on a geological timescale instead of a daily one. When we think about memory in human terms, it's deeply tied to visual detail and predictable physical landmarks. In Horizon Deep, both of these things fall away. The result is an environment where memory, whether human or mechanical, is difficult to establish. A submersible might descend into one region, take measurements, and then return a year later only to find that the same spot looks different. Without clear landmarks or consistent lighting, it becomes hard to tell whether the environment truly changed or whether the vantage point did. Scientists call this the challenge of repeatability. It's not that they can't capture data, it's that they can't always confirm whether the data represents a stable environment or a temporary condition. Another challenge is the sheer monotony of the surroundings. To human eyes, the deep ocean looks repetitive. Large expanses of soft sediment, occasional rocks, and the rare appearance of a creature. When every direction looks similar, navigation becomes difficult. GPS doesn't work, visual cues don't exist. Sonar readings can be ambiguous. Even compass readings can become complicated because magnetic minerals in the seafloor can interfere with measurements. Just moving from one point to another requires careful planning and frequent recalibration. Every movement must be controlled, and every path must be chosen slowly. If you imagine what this feels like from the perspective of a deep-sea vehicle, it becomes clear why exploration is limited. Every meter of travel takes effort. Every measurement requires stability. Every observation depends on lights, sensors, and equipment that need to remain functional under crushing pressure. And the deeper the vehicle goes, the more likely it becomes that something will malfunction. Engineers designing these machines have to account for dozens of forces that rarely matter on land. Materials must resist deformation. Electronics must remain insulated. Batteries must withstand pressure without swelling or rupturing. Even cables need reinforcement, because pressure can force water into microscopic gaps that wouldn't exist on the surface. While all of this creates enormous difficulty for exploration, it also explains why the deep ocean remains one of the last places on Earth where the environment itself shapes everything that happens there. Humans can study it, but they can't change it. They can reach it momentarily, but they can't stay long. They can build machines to descend, but those machines carry limitations that the environment immediately exposes, and yet Horizon Deep holds information about Earth's history that can't be found elsewhere. Sediment accumulates in layers that stretch back millions of years. Chemical signatures reveal changes in the planet's climate. Microorganisms adapt in ways that challenge our understanding of biology. All of this exists in a world that barely interacts with the surface except through the slow settling of organic material. As we keep moving through this topic, each layer of explanation begins connecting to the next. The absence of light changes how organisms live. The slow pace of life changes how ecosystems form. The difficulty of navigation changes how research is conducted. The fragility of equipment changes how often data can be collected. None of these things exist in isolation. The deep ocean has a way of tying them all together into one consistent environment, governed by pressure, darkness, and time measured differently. These interconnected factors form the base for understanding why reaching Horizon Deep fully, scientifically and physically, remains out of reach for now. The next stage in this exploration will take us deeper into the specific forces that push back against even our strongest technology. When people talk about the deepest parts of the ocean, they usually focus on the darkness or the cold, but those things are actually the least of the challenges. Darkness is simple. Cold is predictable. Pressure is not. Pressure is the single biggest obstacle that keeps horizon deep beyond our full reach. It behaves in ways that are straightforward on paper, but incredibly demanding in practice. You can calculate it. You can account for it in equations. You can describe exactly how much force it exerts at a given depth. But none of that fully prepares you for how relentless it is. Pressure doesn't ease up. It doesn't give room for error. It doesn't allow the smallest weakness to go unnoticed. It acts on every surface, every seam, every component, every moment. Understanding the magnitude of deep ocean pressure begins with something most people rarely think about. Water has weight. We don't feel that weight at the surface because we're surrounded by it in every direction. But the deeper you go, the more water is stacked above you. At sea level, the pressure around you is 1 atmosphere. That's the pressure of the air surrounding your body. For every 10 meters you descend, 1 more atmosphere is added. At a few hundred meters, the pressure is already strong enough to crush many everyday objects. At several thousand meters, it becomes powerful enough to destroy equipment that would seem sturdy anywhere else. At the depth of horizon deep, more than 10,000 meters, the pressure exceeds 1,000 atmospheres. That means every square inch of the submersible surface is hit by over 8 tons of force. The human body cannot survive that. The strongest ships cannot survive that. Almost nothing we create can survive it without being engineered for that single purpose. That kind of pressure doesn't simply push downward, it pushes inward. Pressure doesn't care about the direction you intend to move, it applies equally on all sides. Imagine placing an object at the bottom of a massive lake of water. That water presses in from every angle, trying to collapse the object into a smaller volume. On land, most structures only have to resist gravity acting downward. In horizon deep, structures must resist compression from all directions at once, and they must do so continuously. No part of the structure can be weak. If you build something with 99% perfection, the remaining 1% becomes the point of failure, instantly and completely. It might sound dramatic to say that a microscopic flaw can destroy an entire deep-sea vehicle, but that is exactly how pressure behaves. It exploits weaknesses with perfect efficiency. A tiny bubble in a weld, a small imperfection in a seal, a slight variation in material thickness. Pressure does not overlook these things. It behaves like a constant test of structural integrity, one that never pauses. This is why deep-sea submersibles designed for extreme depths have spherical pressure hulls. A sphere distributes pressure evenly. Any other shape carries weak points. Even with this design, the materials used must be incredibly thick and incredibly strong. Steel works up to a point. Titanium works better, but even titanium has limitations. Composites and ceramics offer advantages in some areas and disadvantages in others. The deeper the mission, the fewer materials remain usable. At the depth of horizon deep, the list becomes very short. When you look at a deep-sea submersible designed for the deepest trenches, you might notice how small the pressure hull is compared to the rest of the vehicle. That's not aesthetic, it's required. The more surface area the hull has, the more pressure it must resist. Keeping it small reduces the chance of failure. Even inside the vehicle, the pressure is a constant concern. Any equipment placed within the pressure sphere must operate in a tiny space because expansion outward would require the hull to become larger, which would make it weaker. That's why deep-sea explorers often refer to these vessels as cramped. They aren't cramped by choice. They're cramped by physics. If humans were somehow able to descend without the protection of a pressure hull, the experience wouldn't last long enough to describe. The pressure would collapse the air cavities inside the body almost instantly. Lungs, sinuses, and the digestive tract would be the first to fail. Blood vessels would follow. Bones would withstand more than soft tissues, but even bones would not survive the extreme compression. There's no method for adaptation here. Unlike high-altitude environments where the body can adjust to lower oxygen, or extreme temperatures where the body can regulate itself over time, deep ocean pressure has no equivalent biological workaround. Every creature that lives in the deepest trenches evolved over millions of years to handle these conditions. Those adaptations include soft bodies with few or no air pockets, flexible tissues, and biochemical structures that resist compression. Humans, by contrast, evolved for life at the surface. There is no version of the human body that can manage this environment. That's why we rely entirely on machines. Machines, however, face their own limitations. Pressure doesn't only affect structure, it affects function. Electronics must be shielded, connectors must be pressure balanced, batteries must be built to avoid deformation. Even the oils used inside hydraulic systems must be selected carefully because pressure can change viscosity in ways that cause failure. Radio waves cannot travel through water at these depths, so communication becomes limited. Even simple tasks like operating a robotic arm or turning on a camera become more complicated under extreme pressure. Every moving part must be protected from compression. Every hinge, bolt, and joint must be designed to resist deformation. One of the most surprising things about high pressure is how it affects materials in subtle ways. Metals become slightly more brittle, glass becomes hazardous, plastics can crack or warp, ceramics can fracture from tiny imperfections. Pressure does not simply crush objects, it also changes their behavior. This means engineers must test components repeatedly before trusting them at depth. Testing takes time, and each failure is expensive. That's why deep-sea exploration advances so slowly. Every improvement requires careful redesign, followed by testing, followed by more redesign. There's no shortcut. Every depth reached safely is the result of years of work. Even when a machine is built perfectly, the pressure of the deep ocean still shapes the mission. That pressure limits the duration of the dive. Pressure limits the size of the payload. Pressure limits how much energy the vehicle can carry. Pressure limits the number of instruments that can operate at once. Pressure limits the maneuverability of the vehicle. It limits everything. That's why missions to Horizon Deep rarely last long. Even with advanced technology, staying at extreme depth drains resources quickly. The lights used to see anything consume power. Sonar systems require electricity. Manipulator arms require careful operation. The heavier the equipment, the harder it is to descend and ascend. Every decision becomes a matter of efficiency. And yet, even after all these precautions, pressure sometimes wins. Vehicles have been lost. Instruments have been crushed. Unmanned probes have vanished without explanation. When researchers retrieve damaged equipment, the damage often looks deceptively simple. A structural collapse can happen so quickly that the vehicle appears almost folded or flattened. Engineers analyze the remains to find the exact point of failure, but sometimes all they can conclude is that pressure found a weakness too small to detect beforehand. This is not discouraging so much as a reminder that the deep ocean enforces its own limits. Another challenge created by pressure involves temperature. Near Horizon Deep, the water is only a few degrees above freezing. That cold combined with pressure affects how machinery behaves. Metal contracts slightly in the cold, altering how well components fit together. Lubricants thicken. Batteries lose efficiency. Pressure amplifies these effects by changing the physical properties of many materials. Engineers must select materials that behave predictably under these combined conditions, not only under pressure alone. Pressure also affects biological research. If scientists collect organisms from the deep without maintaining the pressure around them, most cannot survive the trip to the surface. Their bodies rely on the external pressure to maintain their physiological structure. Some organisms that appear sturdy in the deep become nearly gelatinous at the surface because their tissues adapted to compression. When brought up without pressure-preserving containers, they often deform or collapse. This makes studying them extremely difficult. Scientists must design containers that maintain deep ocean pressure, transport the samples safely, and allow analysis without exposing the organisms to surface conditions. Even when successful, the process is slow and complex. The pressure also shapes the geology of the deep trenches. Rock formations respond differently under intense compression. Sediment settles in layers that compress gradually over time. The fine particles that drift from above become compacted. The motion of tectonic plates continues beneath the trenches, and pressure contributes to the way rocks fold, fault and shift. Even the chemical composition of the water is influenced by pressure. Certain chemical reactions that happen easily at the surface become nearly impossible at depth. Others happen more rapidly. This unique chemistry plays a role in the life that exists here. Microorganisms adapt to these chemical differences, and studying them gives researchers insight into processes that might occur in other extreme environments on Earth and beyond. Pressure also affects how long it takes for things to happen. In the deep ocean, processes that occur quickly on the surface may take years or centuries. Sedimentation is slow but steady. Decomposition happens differently because pressure and cold slow the activity of many enzymes. Geological changes that appear sudden relative to the deep are still extremely slow compared to surface processes. In this sense, time behaves differently, not because the physics of time change, but because the conditions limit the speed of physical and biological processes. That's why the deep ocean can preserve certain structures for long periods. A disturbance caused by a submersible might remain visible for years. Footprints of equipment placed on the seabed have been observed long after the mission ended. Pressure slows everything, not by acting on time directly, but by shaping the environment in ways that restrict movement, energy transfer, and biological activity. Thinking about pressure this way helps explain why exploring horizon deep often feels like trying to operate in a world where the rules we know have been rewritten. It's not that the rules are different, it's that the environment pushes everything to extremes. Gravity remains the same, but buoyancy behaves differently at depth. Light behaves differently because it cannot travel far. Sound behaves differently because pressure changes how waves move through water. Even simple actions like collecting a rock or recording a measurement require planning and redundancy because failure is always an immediate possibility. Pressure also constrains how often missions can occur. Each expedition requires not only a submersible but a support ship, trained personnel, technicians, engineers, and scientists. These missions are expensive, and the equipment must undergo extensive inspection after each dive. Even small scratches or dents can compromise the structural integrity of the vehicle. If any flaws found, repairs must be made before the next mission. Sometimes entire pressure hulls must be replaced or rebuilt. These repairs take months. Funding must be secured. Weather must cooperate. All of this limits how frequently expeditions reach horizon deep. Another aspect worth considering is that pressure increases risk even during ascent. When a vehicle begins its journey back to the surface, the pressure decreases gradually. Any trapped gases expand during this ascent. Equipment must be designed to release pressure carefully. If a valve sticks or a chamber fails to adjust, the expanding gas can damage the structure or cause a malfunction that jeopardizes the entire vehicle. Engineers design complex systems to manage this change, but the risk never disappears entirely. Despite these challenges, exploration continues because Horizon Deep represents one of the last major frontiers on Earth. Each mission brings back data that helps researchers understand not only the deep ocean, but the planet as a whole. Geological samples help reconstruct Earth's history. Biological samples reveal adaptations that challenge assumptions about life's limits. Chemical data informs models of ocean circulation. Every new piece of information connects to larger scientific questions. But pressure ensures that progress remains slow and uneven. Technology improves, but the fundamental challenge remains unchanged. As the discussion moves forward, the next part of this descent will look at how the absence of light, combined with the extreme pressure, creates an environment where darkness isn't just a visual condition, but a limiting factor for movement, behavior, and exploration. The interaction between these forces forms the backdrop for understanding why Horizon Deep remains almost untouched despite decades of effort. When we move deeper into the region surrounding Horizon Deep, one of the first realities that shapes every observation is the absence of natural light. People often describe deep ocean darkness as complete, but that word doesn't really convey what it's like. On land, even at night, there are countless sources of light. The moon, stars, city lights, reflections off buildings, headlights, lamps, phones, screens. Darkness on the surface of Earth is rarely absolute. Even caves have faint ambient light near entrances. But the deep ocean is an environment where natural light does not exist at all. It isn't dim or faint, it isn't shadowed, it isn't a place where your eyes adjust after a moment. It's an environment where light has no presence because it simply cannot reach these depths. When sunlight enters the ocean, it begins to lose strength immediately. Each wavelength is absorbed at a different rate. Red disappears first, followed by orange, yellow, green, and eventually even deep blue. By the time you reach a depth of a few hundred meters, only fragments of blue remain. Go deeper, and those fragments vanish entirely. Below roughly 1,000 meters, sunlight is gone. Everything beneath that level is separated from visible light the same way underground caves are separated from the sky. But the difference is that the ocean layers above become so thick and dense that no amount of eye adjustment can compensate for the darkness. This isn't a dramatic or frightening condition. It's not the kind of darkness associated with danger. It's more like an environment where visibility is not a feature of the world. If you were to descend without lights, you wouldn't see a faint outline or a shadow. You wouldn't see the glow of your own hands. You wouldn't perceive shapes. The darkness is so complete that it removes the visual part of perception entirely. The result is an environment where navigation, orientation, and movement must rely on something other than sight. This forces every living thing in the deep to evolve around different sensory inputs, and it forces human explorers to bring artificial light with them. But that artificial light changes the environment the moment it appears. The strange part about this darkness is that it doesn't feel dramatic when described by researchers. They often talk about it in practical terms. Light does not exist here, therefore other senses must compensate. But for most people hearing about it for the first time, the idea can be hard to grasp. We're used to light being present, even if faint. Our brain expects some kind of visual input in every direction. When that input disappears completely, our ability to form a mental map collapses. On the surface, visual memory helps us navigate. In the deep ocean, memory tied to vision has no use. There are no landmarks, no recognizable shapes, no outlines to distinguish one area from another. Even bioluminescence, often imagined as a bright light against the darkness, functions at levels far dimmer than most people expect. The glow of deep-sea organisms is usually faint and short-lived. Some flashes last milliseconds. Some pulses are no brighter than a weak LED. The colours differ from surface light because they are tuned for underwater visibility, but they rarely illuminate the environment in any meaningful way. They are signals, not lanterns. Even large organisms that emit bioluminescent patterns don't create anything resembling visibility. Their light may reach a few inches or a few feet at most. Beyond that, darkness resumes immediately. This environment affects everything, including the way creatures move. Without light to orient them, many species rely on pressure-sensitive structures that detect movement in the water. Others rely on chemical cues. Some use electrical fields. A few have highly sensitive eyes adapted to capture tiny amounts of bioluminescence. But these eyes are tuned for specific wavelengths and often appear oversized or oddly shaped compared to surface animals. These adaptations don't create a visible world. They allow organisms to function without needing one. When humans send submersibles into these depths, they bring lights powerful enough to penetrate the darkness for several meters, sometimes more. But these lights do not replicate anything the animals normally see. The beams can startle wildlife or cause it to retreat. They can alter the colour or behaviour of organisms that rely on darkness for survival. They can also stir sediment, making visibility worse than before. Submersibles must balance the need to see with the need to avoid disturbing the environment. Even with careful operation, the moment artificial light enters the deep, it changes what is being observed. The relationship between light and observation becomes a problem in deep-sea research. Because light reveals only a limited area, researchers have to move slowly. If they move too quickly, they might miss important details or disturb sediment that obscures the surroundings. But even moving slowly, the illuminated cone from the submersible's lamps shows only a small fraction of the environment. The rest remains hidden. This creates a narrow window of visibility that shifts with each movement. The constant effort to see what lies ahead becomes one of the limiting factors in how far and how safely a submersible can travel. There is also a practical issue with light at these depths. The deeper a vehicle descends, the more power it needs to operate its lights. Light spreads and weakens quickly in water. To illuminate even a small area, electrical output has to increase, but power is limited because batteries can only carry so much charge, and larger batteries increase the size of the vehicle, which increases pressure exposure. Engineers have to balance visibility with power consumption and structural design. Sometimes researchers choose to reduce their lighting to conserve energy, but this reduces the effectiveness of the dive. It's a constant trade-off between seeing and surviving. Darkness also affects how sound is used in exploration. Because light cannot penetrate far, sonar becomes essential. Sonar maps the environment using sound waves, but interpreting sonar data in deep trenches is far more complex than in shallow waters. Temperature, salinity, and pressure influence how sound travels. In the deep ocean, sound can bend, refract, or reflect in ways that make it difficult to interpret. Soft sediment absorbs sound unevenly. Rocky surfaces scatter signals. Even the shape of the trench can distort sonar readings. As a result, mapping horizon deep requires careful calibration. A small misinterpretation can cause a submersible to misjudge a slope or mistake a rock formation for open space. The darkness becomes not just a visual absence but an obstacle that affects data collection, safety, planning, and navigation. Human technology is fundamentally designed around environments with at least some natural light. Cameras rely on it. Sensors rely on it. Even mechanical instruments are often easier to operate when visibility is present. But in Horizon Deep, none of that applies. Darkness becomes a limiting factor, not because it is frightening, but because it eliminates most of the sensory cues humans depend on. Another aspect of the deep-sea darkness is its effect on distance and perception. When you shine a light in water, the illuminated area appears smaller than expected because water absorbs and scatters light quickly. A rock that looks close may be several meters away. A slope that looks gradual may be steeper than it appears. Even depth perception becomes unreliable. The lack of shadows makes it difficult to distinguish between protrusions and depressions. Flat surfaces can look uneven. Uneven surfaces can look smooth. Pilots of deep-sea vehicles learn to rely on instrumentation more than their eyes because visual perception becomes misleading. Biologists face another challenge in studying organisms in deep darkness. Many deep-sea species behave differently when exposed to artificial light. Some retreat immediately, some cease natural behaviors, some freeze in place. A few approach out of curiosity or confusion, but those reactions may not represent their typical behavior. Because of this, studying deep-sea life without altering it becomes nearly impossible. Researchers must interpret their observations knowing that the presence of light and the noise of the submersible may distort their findings. Even the colours of organisms cannot be accurately perceived here. Many deep-sea species appear bright red when brought to the surface, but in their natural habitat, red light does not exist. That means they appear black or nearly invisible in the deep. Their red coloration serves as a form of camouflage, but artificial light reveals it. So when researchers see a bright red shrimp or fish under a submersible's beams, they must remember that the organism is not supposed to look that way in its natural environment. This complicates identification and classification. Darkness also influences the geological features of horizon deep. Sediment accumulates on the seafloor through a slow rain of particles from above. Without strong currents or disturbances, this sediment can remain undisturbed for long periods. When submersibles approach too closely, their thrusters can stir up the sediment, creating clouds that take a long time to settle due to the dense water and minimal water movement. This snow effect can obscure visibility for minutes or hours, forcing missions to halt or relocate. Even small disturbances become significant because the environment lacks the natural motion needed to clear the water quickly. Another rarely discussed consequence of deep ocean darkness is how it influences the engineering of sensors. Cameras must be designed for low light or no light conditions, often requiring lenses and housings that withstand pressure while maintaining clarity. Lights must be arranged to minimize glare and reflection off particles in the water. Sonar arrays must compensate for distorted acoustics. Temperature sensors, chemical detectors, and pressure gauges must be placed where they can function without interference. Every instrument becomes a specialized piece of equipment requiring testing and calibration. The absence of light also affects long-duration exploration. Autonomous vehicles that operate without human control must navigate an environment where visibility is almost zero. They rely entirely on programmed paths, sonar, and internal sensors. But any unexpected object, a rock, a slope, a trench wall, can pose a risk. Because the vehicle cannot see, in the usual sense, it must operate cautiously, limiting its speed and distance travelled. This slows the mission and reduces the amount of ground that can be covered in one dive. Mapping the trench systematically becomes extremely time-consuming. In many ways, darkness enforces a kind of patience. It slows exploration, limits data, and requires careful planning. Researchers cannot rapidly scan the environment the way satellites scan land or shallow water. They cannot rely on continuous video the way they might on land. Every image captured has to be analysed carefully. Every sonar reading must be interpreted within a complex context. Every sample must be retrieved without disrupting the environment more than necessary. Another factor worth noting is the psychological impact of deep ocean darkness on human explorers. Those inside submersibles often describe a strange sensation of disconnection from the outside world. They can see only what their lights reveal, and beyond that lies a void of unlit water. Some compare it to travelling through a tunnel with no walls, no ceiling, and no floor. But this sensation doesn't cause fear. Instead, it creates a heightened awareness of the vehicle's interior. The focus shifts inward. Instruments, controls, and the immediate surroundings inside the vessel become the explorer's reference points. The outside world becomes something approached through measurements rather than through sight. As exploration continues, the darkness shapes every decision. It determines how close a submersible can approach the seafloor. It dictates how fast it can move. It influences how researchers interpret every piece of data. It affects the design of equipment. It changes how organisms behave. It alters the way sound is used. It restricts the reach of light. It slows the pace of sampling. In this way, the darkness becomes not just a background condition, but a defining feature of the environment. Even after decades of exploration, the darkness remains one of the key reasons why Horizon Deep is still poorly understood. Technology improves, but the fundamental problem does not change. As long as light cannot reach these depths, and as long as artificial light remains limited by power, pressure, and environmental impact, exploration will remain slow and incomplete. The next part of this exploration will move into the lives that inhabit these depths. Organisms that have adapted not only to pressure and cold, but also to an environment where light plays virtually no role at all. Their survival reveals how life can develop in extreme places, and studying them helps build a clearer picture of the deep ocean's complexity. When the discussion shifts from the physical environment of the deep to the organisms that inhabit it, the picture becomes even more complex. Life in the region surrounding Horizon Deep does not resemble the energetic, colourful or fast-moving ecosystems near the surface. It doesn't rely on sunlight, rapid reproduction, or abundant food. Instead, the organisms here are shaped by conditions that leave little room for waste. Every movement, every adaptation, every feature serves a direct purpose that supports survival in an environment where pressure, cold, and darkness define every moment. These conditions create species that appear strange, efficient, and sometimes deceptively simple. Yet behind their simplicity is a level of adaptation that far surpasses what most environments require. The organisms found here are often referred to as extremophiles, but that label can be misleading. While their environment is extreme by surface standards, for the species that evolved here, these conditions are simply normal. They do not think of themselves as living in a harsh environment. They are not struggling against it. They are shaped by millions of years of adaptation that make them perfectly suited for a world where almost every other form of life would fail immediately. This perspective is important because it shifts the way we think about deep-sea biology. These creatures are not barely surviving. They are thriving within a set of rules entirely different from the ones that govern life on land. One of the key features shared by many deep-sea species is the absence of rigid structures. Creatures living near Horizon Deep tend to have soft, flexible bodies with few or no air-filled spaces. This adaptation helps them withstand the intense pressure. If an organism's body contains air pockets, those pockets would collapse under compression. That's why fish living in surface waters cannot survive in the deep. Their swim bladders, which help them regulate buoyancy, would collapse instantly. In contrast, deep-sea fish often lack swim bladders entirely. Instead, they rely on oils, lipids, or gelatinous tissues to manage buoyancy. These tissues are not affected by pressure in the same way air is, allowing the animals to maintain stability. Flexibility becomes an advantage in this environment. Soft tissues withstand pressure better than rigid structures. Many creatures that appear gelatinous are not fragile at all. They are adapted to maintain shape under incredible compression. Their bodies lack the rigid skeletons common in surface species because a rigid skeleton offers no advantage in an environment where movement is slow and rapid. Speed is rarely necessary. Instead, muscles and connective tissues are arranged to allow careful precision rather than quick bursts. Another characteristic of deep-sea organisms is their slow metabolism. In the deep ocean, energy sources are limited. Food arrives in the form of marine snow, a slow drift of organic particles from higher layers. Occasionally, large food falls occur, dead whales, fish, or plant matter sinking to the ocean floor. But these events are unpredictable. To survive in a world where nutrients are scarce, organisms have evolved metabolic systems that operate slowly and efficiently. Some species live decades longer than their shallow water relatives. They grow at a rate that might seem impossibly slow to surface dwellers, but slow growth conserves energy. Even reproduction is gradual. Many species produce fewer offspring, each one adapted to survive long periods with minimal food. Light plays no role in their behaviour, so sensory systems rely on other cues. Some deep-sea organisms possess highly developed lateral lines, structures that detect slight movements or vibrations in the water. These lines allow them to sense nearby organisms without seeing them. Others have organs that detect electrical signals produced by muscle movement in potential prey. A few species have eyes that remain sensitive to small flashes of bioluminescence, enabling them to detect signals from prey or predators. But these eyes are tuned for faint, specific wavelengths. They are not used for general visibility. The role of bioluminescence becomes more significant at these depths. Many creatures produce light through chemical reactions, often controlled by bacteria living inside specialized organs. While the lights these organisms produce are dim, they serve important functions. Some species use bioluminescence to confuse predators. A quick flash of light distracts or startles nearby creatures, creating an opportunity to escape. Others use it to communicate, especially during mating. Specific patterns of blinking help animals recognize members of their species. Some predators use bioluminescent lures. These lures mimic small prey, attracting other organisms close enough to catch. Even though light is scarce, these brief signals give deep-sea animals a navigational advantage. One of the more surprising things about life in horizon deep is the presence of species with adaptations that seem counterintuitive. For example, many deep-sea fish have small or reduced eyes, yet some possess oversized pupils. This contrast arises because even though light doesn't exist naturally, bioluminescence still provides enough visual information to warrant specialized eyes. Large pupils collect more light, even if the amount is extremely small. These eyes help detect faint glows from prey or predators. On the other hand, reduced eyes sometimes appear in species that rely more on sensing vibration or chemicals. In conditions where sight becomes unreliable, investing energy in maintaining large eyes is unnecessary, so evolution favors reductions. Another adaptation common in deep-sea species is their unique muscle structure. Because the pressure is so high, muscle fibers behave differently. They cannot contract rapidly as they do in shallow waters. Instead, they contract slowly and steadily, allowing precise controlled movement. This is why many deep-sea animals appear to drift or hover rather than swim quickly. Fast swimming requires energy. In an environment where energy is scarce, quick movements are rarely beneficial. The behavior of predators in these depths reflects this slow pace. Predators do not chase prey over great distances. They rely instead on ambush strategies, using minimal movement to conserve energy. Some species bury themselves in sediment. Others drift slowly until their prey comes close enough to strike. In the deep, speed is not a survival advantage. Patience is. Many predators have jaws that hinge outward or teeth that angle inward, allowing them to catch prey with minimal exertion. When food is unpredictable, wasting energy on a pursuit that might not succeed becomes a risk. Reproduction also takes unique forms. Many deep-sea species release eggs or larvae that drift for long periods before settling. These larvae travel upward, sometimes into shallower waters, where food is more abundant. As they mature, they migrate downward, gradually adapting to the increased pressure. This downward migration is not rapid. It can take months or years. The method allows the young to feed in areas with more resources, increasing their chance of survival before they settle into the slow, energy-efficient lifestyle required for life at extreme depths. Chemical adaptations also play an important role. Many deep-sea organisms produce molecules that prevent proteins from collapsing under pressure. Proteins in surface organisms often lose their shape when exposed to high pressure, but deep-sea species have evolved compounds that stabilize their proteins. This biochemical stability is crucial for maintaining function in enzymes and membranes. Without it, their cells wouldn't survive. Understanding these compounds has become an area of interest for scientists studying life in extreme environments, and for biotechnologists exploring new ways to stabilize proteins under industrial conditions. Another fascinating aspect is the structural composition of deep-sea fish bones. Their bones are often less mineralized than those of surface fish. This makes them lighter and more flexible. Hard, dense bones would be liabilities under high pressure. Flexibility becomes a survival advantage. Some deep-sea fish even have skeletal structures that remain partially cartilaginous, allowing them to withstand the compressive forces of their environment. The diversity of species in horizon deep might seem limited compared to surface waters, but each species carries a unique combination of adaptations. Some are small and gelatinous, drifting slowly through the water. Others are elongated with carefully aligned muscles that allow controlled movement. A few are predators equipped with oversized jaws and sharp teeth, designed to catch prey with a single efficient motion. In this environment, even teeth behave differently. Many are angled to prevent prey from escaping once captured. Because prey encounters are rare, losing a captured meal would be wasteful. A particularly interesting group of organisms in these depths are amphipods. small crustaceans that have adapted to survive the intense pressure. Amphipods at extreme depths often have translucent bodies. Their exoskeletons lack the rigid structure of their shallow water relatives. Their diet relies heavily on organic material that drifts from above. Some amphipods have been found feeding on carcasses that reach the deep, demonstrating how important food falls are for deep-sea communities. A single large carcass can support an entire ecosystem for months. Microorganisms play an equally important role. Bacteria and archaea adapted to high pressure, known as piezophiles, form the base of the food web. These microorganisms break down organic matter efficiently in cold, high-pressure environments. Some even use chemical energy sources such as methane or hydrogen sulfide, especially near hydrothermal vents. These chemical processes allow life to persist in areas where organic material is scarce. Microorganisms in horizon deep provide nutrients to larger species, support decomposition, and influence chemical cycles in the ocean. Their presence is vital for maintaining ecosystems that survive with so little external input. Another organism commonly associated with deep waters is the snailfish. Snailfish found near the deepest trenches have bodies adapted to withstand extreme pressure. Their skulls are small and delicate. Their muscles contain compounds that maintain flexibility under pressure. Their digestive systems function efficiently with minimal energy. These fish are rarely seen on camera because they tend to remain near the seafloor, where they feed on amphipods and other small organisms. When researchers do capture footage of them, the fish often appear calm and slow-moving. They are not stressed or struggling. They are simply living in conditions that suit them. It's easy to assume that the deep sea supports only simple organisms, but this isn't entirely true. Complexity exists here, just expressed differently. Instead of vibrant colours or elaborate body shapes, complexity appears in chemical pathways, muscle adaptations, metabolic systems, and sensory mechanisms. Deep-sea life demonstrates that complexity doesn't always look dramatic. Sometimes it appears subtle or understated because the environment favours efficiency over display. Many deep-sea organisms also serve as indicators of environmental change. Because their habitats change slowly, they are sensitive to disturbances from above. Tiny shifts in temperature, chemical composition, or nutrient input can influence deep-sea populations. Scientists study these organisms to understand long-term environmental trends. Their slow growth and long lifespans make them reliable markers of change that surface species might not reflect accurately. As exploration continues, researchers often encounter species that defy expectations. Some have been found with antifreeze proteins similar to those found in polar fish. Others contain compounds not seen in surface species. Some produce bioluminescent signals that vary in pattern and intensity. Each discovery adds another piece to the puzzle of how life persists, where conditions appear almost incompatible with survival. Another factor shaping deep-sea life is isolation. The organisms living in horizon deep exist far from shallow ecosystems. They do not mix with surface populations. Genetic exchange is minimal. This isolation creates distinct lineages with traits that may not appear anywhere else. It also means that deep-sea species often differ significantly from their close relatives. Over millions of years, these differences accumulate, creating organisms uniquely suited to their environment. This isolation also influences behavior. In many deep-sea species, territoriality is rare. There isn't enough energy for territorial disputes. Large territories offer no advantage. Instead, creatures tend to roam slowly or remain in small, stable areas. Social structures are simpler. Mating encounters are rare and often rely on chemical cues rather than displays or competition. Some species have evolved strategies where males remain attached to females permanently to ensure reproduction. These strategies reflect the difficulty of finding mates in a vast, low-density environment. One of the most important roles deep-sea organisms play is recycling nutrients. When organic matter drifts from above, microorganisms break it down. Larger organisms consume these microorganisms. Predators feed on smaller creatures. Each stage contributes to nutrient cycling. Without these processes, organic material would accumulate on the seafloor without decomposition. Deep-sea organisms help maintain balance in the ocean, influencing larger chemical cycles that affect the entire planet. Studying these creatures helps researchers understand limits of life. The adaptations seen here inform theories about life on other planets. If organisms can survive deep-sea pressure, extreme cold, and total darkness, then life may exist in environments once considered inhospitable, such as the oceans beneath the ice crusts of Europa or Enceladus. Deep-sea biology shapes how scientists search for extraterrestrial life. The combination of pressure, cold, darkness, and limited food creates a living system unlike any other. Each organism represents a solution to the challenges of this environment. These solutions are not dramatic or showy. They're efficient and specialized. They reflect millions of years of evolution within constraints few ecosystems impose. As we continue this exploration, the next stage will examine how even the most advanced machines cannot fully replicate the adaptations these organisms possess, and why the technology designed to reach Horizon Deep remains vulnerable to the same forces these organisms endure naturally. The deeper we go into understanding Horizon Deep, the more obvious it becomes that the technology humans build is at a fundamental disadvantage. When you compare our machines to the animals that live here naturally, the contrast is striking. Deep-sea creatures endure pressure, cold, and darkness effortlessly because they evolved specifically for those conditions. Machines, by contrast, are built in environments where air surrounds them, where temperature is controlled, where pressure is negligible, and where light is taken for granted. They are designed for places that behave very differently from the deep ocean. No matter how advanced they are, machines carry assumptions built into them, assumptions based on the surface world. The deep ocean does not share those assumptions, and the mismatch becomes obvious the moment technology begins its descent. A machine that works perfectly on land can fail within minutes at just a few hundred meters below the surface. Bolts loosen, seals deform, electronic short circuit. Things that seem sturdy in normal conditions become fragile when exposed to pressure. Even materials considered highly durable behave differently in the deep. It's not simply a matter of making machines stronger. Strength alone doesn't solve the problem. Machines must remain functional while resisting pressure from every direction, surviving near freezing temperatures, operating in total darkness, and communicating without the use of radio signals. That requires compromises, and each compromise creates new limitations. One of the first limitations becomes clear as soon as a machine starts descending: size. A large machine has more surface area, and more surface area means more pressure. Even if the hull is incredibly strong, the forces acting on it increase with every additional square inch. That's why deep-sea submersibles tend to be small, round, and compact. They can't be built in the sleek or elongated shapes used for shallow water vehicles. Those shapes may be hydrodynamic, but they introduce structural weak points at depth. Round shapes distribute pressure evenly. They're harder to build, harder to maintain, and far less spacious, but they reduce the chance of catastrophic failure. Inside these small, spherical hulls, space is so limited that every piece of equipment must be carefully chosen. There's no room for redundancy beyond the essentials. If something breaks, once the submersible reaches extreme depths, repairs are impossible. Machines must survive the journey down, complete the mission, and return safely without intervention. That constraint shapes every decision engineers make. They select only what is absolutely necessary. They eliminate features that might consume extra power or add unnecessary weight. They build systems that can function under extremely restricted conditions. Even with all of this, failures still occur. One of the most delicate parts of any deep-sea machine is its electronics. Electronics rely on specific operating conditions. They must remain dry, remain insulated, and maintain stable temperatures. In Horizon Deep, every one of those requirements becomes a challenge. Pressure tries to force water into even microscopic openings. Temperature tries to destabilize sensitive components. Insulation materials behave differently under high pressure. Wires become brittle. Connectors loosen. Power distribution becomes less predictable. Engineers counter these issues with pressure-resistant housings, specialized cables, and sealed connectors, but each solution adds weight and complexity. Another major limitation is communication. On land, machines can communicate wirelessly. They use radio waves, satellites, or direct wireless networks. Underwater, radio waves fade almost immediately. Even at shallow depths, wireless communication becomes nearly impossible. Sound becomes the primary tool for communication, but sound travels slowly and behaves unpredictably in the deep ocean. Temperature layers bend sound waves. Salinity affects their speed. Pressure changes how they reflect. That means the deeper a machine goes, the harder it becomes to control remotely. Commands take longer to reach the vehicle. Responses return slowly. The machine may drift or move slightly before a command is processed. This delay makes precise control difficult, especially in tight spaces. Because of this, some deep-sea vehicles operate autonomously. They follow pre-programmed paths and perform tasks without direct human guidance. But autonomy introduces new risks. A machine might misinterpret its surroundings. A slope that appears stable on sonar may be unstable. A trench wall may appear farther away than it really is. A sudden change in depth may confuse sensors. If an autonomous vehicle miscalculates, no human can intervene in time to prevent damage. That's why these vehicles move slowly, gather data cautiously, and avoid unnecessary risks. But slow operation reduces the amount of area they can explore in a single mission, limiting scientific return. Navigation adds another layer of difficulty. Without GPS, machines rely on internal systems to track their position. They use inertial measurement units, compasses, sonar, and depth sensors. But each of these tools becomes less reliable as pressure increases. Magnetism can behave differently near certain rocks on the seafloor. Inertial systems drift over time. Sonar maps can be distorted by uneven sediment. Even depth sensors may become less accurate under extreme conditions. This means that a machine might not know its exact location once it reaches the deepest points. Without precise location data, mapping the environment becomes slower and less reliable. Lighting is another factor. Machines require artificial light to see anything in the deep, but strong lights consume power quickly. Power limits how long a vehicle can remain below. A submersible must balance lighting needs with power constraints. If the lights are too bright, they may scare away organisms or distort the environment. If they are too dim, the machine may miss important details or have difficulty navigating. The need for light, combined with limited power, forces vehicles to prioritize where and when lighting is used. Often, they capture only short glimpses of the environment, leaving large areas unobserved. Pressure influences how materials behave, but it also influences how machines move. Thrusters must be designed to operate in dense water. They cannot create too much turbulence, or they risk stirring up sediment that reduces visibility. But they must create enough force to maneuver. Too much thrust wastes energy. Too little makes navigation imprecise. Designing thrusters that can operate effectively at extreme depth is a challenge. Many deep-sea vehicles move slowly not because they are incapable of speed, but because speed is inefficient or dangerous in this environment. Power supply is another constraint. Batteries must function at low temperatures and under pressure. Some battery types deform or malfunction under these conditions. Others lose capacity. Engineers must choose batteries that remain stable, but those batteries often store less energy than other types. This limits how far a vehicle can travel and how long it can stay at depth. Recharging batteries underwater is not practical, and swapping them out requires bringing the machine back to the surface, which takes hours. This reduces the number of dives possible during an expedition. The mechanical arms on remotely operated vehicles illustrate another challenge. Manipulating objects in deep-sea darkness requires precision, but high pressure affects hydraulic systems. Fluids behave differently. Valves must be reinforced. Moving parts must be designed to withstand compression. Even with careful engineering, robotic arms in the deep often move slowly with limited dexterity. Picking up a fragile organism or taking a delicate sample becomes a careful process. A task that would take seconds on land may take minutes in the deep. Sometimes the machine has to back away and approach again because sediment clouded the area. Every action is slowed by the environment. The terrain in Horizon Deep adds further complications. The seafloor is not flat. It contains ridges, slopes, trenches within trenches, and uneven sediment. Some areas are soft, some are rocky, some are unstable. Machines risk becoming stuck or damaged if they approach the seafloor too closely. A thruster might accidentally blow sediment upward, reducing visibility. A misjudged movement might push the vehicle against a rock. A sudden shift in the terrain from minor geological activity might trap a robotic arm or destabilize the machine. Navigating this terrain requires constant attention to sensor readings and careful control of movement. Despite all these challenges, modern deep-sea vehicles are capable of remarkable feats. They can reach depths once thought impossible. They can take samples, record video, and collect data. They can operate in environments that would destroy nearly anything else we build. But even with their advancements, they cannot survive here in a sustained way. A machine built to reach Horizon Deep cannot spend days exploring it freely. It can only visit briefly. It must return to the surface before its power runs out or its structure weakens. It is designed to survive, not to live here. This is the key difference between machines and deep-sea organisms. The creatures that thrive in the deep are not resisting the environment. They are part of it. Their bodies allow them to exist effortlessly, where machines must be carefully engineered to withstand every force. Their metabolism aligns with the slow pace of the deep. Their senses match the environment. Their structures work with pressure, not against it. They are the product of millions of years of evolution in a place where machines last only hours. It might seem surprising that many creatures living in extreme depth appear delicate. Some are transparent, some look soft, some drift rather than swim. But those traits are strengths in this environment. A soft body is not a weakness. It's a structural adaptation that prevents collapse. Slow movement conserves energy. Lack of bones reduces vulnerability to pressure. Machines cannot adopt these qualities. A machine cannot be soft without losing structure. It cannot drift without losing control. It cannot be small without limiting its capabilities. This is why no matter how advanced our technology becomes, it always faces difficulties here. Temperature also affects machines differently than it affects organisms. Many deep-sea creatures maintain function at low temperatures because their biochemical processes evolved for cold environments. Machines must compensate artificially. Metals become brittle in cold conditions. Batteries lose performance. Hydraulic fluids can thicken. Insulation becomes crucial. Engineers design systems to work at these temperatures, but those systems require energy and careful construction. A machine that malfunctions due to cold has no way of repairing itself or adapting. An organism simply lives at that temperature as its natural state. The slow pace of the deep also challenges machines. A machine designed to operate efficiently in rapid or variable environments may struggle in a place where everything moves slowly. Sensors may detect fewer changes than expected. Movement may feel inefficient. The vehicle might appear to drift or respond sluggishly because the water is so dense. Engineers cannot design a machine to mimic the slow, energy-efficient movement of deep-sea animals, because machines rely on mechanical power, not biological processes. The environment resists fast movement and demands patience, but machines are built for tasks that require speed or precision. Even the descent and ascent challenge machines. Reaching Horizon Deep takes hours. During descent, pressure increases steadily. During ascent, pressure decreases. Both transitions place stress on the vehicle. Engineers design pressure compensation systems to handle these changes, but those systems add complexity. If any of them fail, the machine may suffer damage. Organisms do not experience this stress. They remain at depth or migrate slowly, allowing their bodies to adjust gradually. Machines must travel the entire vertical span in one continuous journey, making them vulnerable during transitions. Time becomes another limitation. A machine can only operate for as long as its power lasts. A deep-sea dive may last 8 to 12 hours, but only a small portion of that time occurs at the bottom. Most of it is spent descending or ascending. That means even the most advanced machines spend little actual time exploring. This restricts what they can accomplish. A few hours is not enough to observe long-term behavior or to study slow-moving biological processes. Machines must prioritize what they examine, often leaving large areas unexplored. Pressure also affects how machines handle samples. When collecting organisms or sediment, the equipment must be designed to maintain the environment's pressure. Without pressure maintenance, samples may be damaged or altered during ascent. This limits what can be studied. Some organisms arrive at the surface intact. Others collapse or deform. Some chemical conditions cannot be preserved. Machines must solve these challenges by using pressure-retaining containers, but those containers are heavy and limited in capacity. The need to preserve samples restricts how much can be collected during a single dive. Mechanical fatigue is also more significant at depth. Pressure causes materials to compress slightly, and repeated compression and decompression can weaken them. After each dive, engineers must inspect every part of the vehicle. Even small cracks or distortions indicate potential failure on the next dive. Maintenance takes time. Repairs require specialized materials. Rebuilding components is expensive. These limitations mean that deep-sea vehicles cannot be used frequently without constant upkeep. Another reason machines struggle here is the unpredictability of the deep ocean environment. The conditions appear stable, but local variations can occur. Changes in temperature, currents, or chemical composition may affect sensors or systems. If a machine enters an area with unexpected conditions, it may not have the flexibility to adapt. Deep-sea animals adjust automatically because they evolved under these variations. Machines rely on predetermined settings. When considering all of these factors together, it becomes clear why machines cannot truly thrive where these organisms live naturally. Every element of the deep ocean environment — pressure, darkness, cold, density, limited energy — works against mechanical function. Life survives here by aligning with those forces. Machines survive only by resisting them, and resistance requires energy, careful design, constant maintenance, and limited operation. Even as technology improves, this fundamental mismatch persists. Machines may reach deeper, last longer, and gather more data, but they cannot become part of this world. They remain visitors. Their presence is temporary. Their capabilities are limited by physics, engineering, and the practical realities of operating in an environment humans did not evolve to understand firsthand. As we continue in the next section, the focus will move into how human limitations contribute to the difficulty of deep exploration, and why even the most robust machines require human oversight that becomes increasingly difficult the deeper the descent goes. One of the most important things to acknowledge when talking about exploring Horizon Deep is how unsuited the human body is to these depths. Machines fail for mechanical reasons, but humans fail for biological ones. The limitations are not subtle. They are immediate, absolute, and non-negotiable. People sometimes imagine that the reason we cannot explore the deep ocean directly is because we haven't built the right kind of diving suit, or because we need better technology, but the truth is far more straightforward. Human physiology is designed for life at sea level. Our lungs, our blood vessels, our bones, our nervous system, and even the chemical reactions that keep us alive all depend on an environment with low pressure, abundant oxygen, and predictable sensory input. The deep ocean removes all of that from the moment the descent begins. The first major challenge is pressure. At the surface, the human body handles 1 atmosphere of pressure easily. We don't feel it because the fluids and gases inside our bodies balance that pressure. But as soon as pressure increases, the balance collapses. Divers experience this even at relatively shallow depths. At 30 meters underwater, pressure triples. This alone can cause discomfort or injury if not managed correctly. Professional divers use pressurized equipment, decompression schedules, and gas mixtures to survive deeper dives. But these methods have strict limits. Beyond a few hundred meters, the pressure becomes so great that no diving suit can protect the wearer. Past that point, even breathing specialized gas mixtures becomes impossible. Oxygen becomes toxic under high pressure. Nitrogen causes narcosis. Helium can create neurological issues. There is no gas mixture that allows a human to breathe safely at extreme depths. This is why submersibles became the only viable method for human exploration. A submersible keeps the internal environment at normal atmospheric pressure, allowing occupants to breathe normally. But this innovation doesn't change the fact that the external pressure is immense. The pressure hull becomes the only thing standing between the human body and an environment that would crush it instantly. The hull must remain flawless. Any crack, deformation, or material weakness puts the crew at risk. Human fragility becomes apparent in the simple fact that survival depends on a thin barrier of engineered material. Even inside a submersible, the human body faces challenges. The confined space can cause discomfort, anxiety, or claustrophobia. The journey down is long and movement is restricted. There's limited ability to stretch, stand, or change position. This might seem like a minor inconvenience, but when the descent lasts hours, physical strain accumulates. Muscle fatigue becomes noticeable. Joints stiffen. Prolonged immobility affects circulation. Submersible designers account for this by including seats and restraints that reduce strain, but there's only so much space to work with. The sensory environment also has an impact. The deep ocean does not provide visual or auditory input that humans are used to. Everything outside the window is dark. The only visible features are those illuminated by artificial lights, and even then the scene is small. The human brain instinctively tries to make sense of surroundings, but the lack of context confuses perception. Without familiar cues, depth and distance become difficult to interpret. Some explorers describe the view as disorienting, not because it's frightening, but because the environment lacks structure. Sound behaves differently as well. Inside the submersible, mechanical noises from pumps, motors and instruments become constant. The hull creaks and groans slightly under pressure. These sounds are normal, but they can be unsettling for people who are not accustomed to them. The knowledge that the pressure outside is many times greater than what the hull is designed to withstand adds psychological stress. Skilled operators understand that these noises do not indicate danger, but the human brain responds instinctively to unfamiliar sounds, especially in environments where the consequences of failure are severe. The cold of the deep ocean also affects humans indirectly. While the submersible protects its occupants, the internal temperature often fluctuates. Heating systems counteract the cold surrounding water, but maintaining a stable temperature can be challenging. Even small drops in temperature can affect comfort, dexterity and focus. If condensation forms inside the vessel, it can create additional issues. Equipment becomes slippery. Vision through windows may become slightly distorted. Small problems accumulate quickly in tight spaces. Another consideration is oxygen. Inside a sealed submersible, oxygen must be supplied, and carbon dioxide must be removed. Humans cannot tolerate high levels of carbon dioxide. Even slight increases can cause dizziness, headaches, or impaired thinking. Deep-sea submersibles use scrubber systems to keep air breathable, but these systems rely on precise chemical reactions and specialized materials. If a scrubber fails, the situation becomes dangerous rapidly. This adds another layer of fragility. Humans depend on an atmosphere that must be carefully maintained through technology. Physical endurance is limited as well. The average deep-sea dive lasts several hours from start to finish. Crew members must remain alert the entire time. They must operate instruments, monitor readings, communicate with the surface team, and make decisions based on incomplete or changing information. Fatigue can impair judgment. Hunger and thirst must be managed because eating or drinking inside a submersible can be awkward and messy. Bathroom needs must be addressed through systems designed for minimal use. These issues may sound trivial, but at extreme depths, even small discomforts or distractions can escalate into real problems. Psychological limitations are often overlooked, but play a significant role in deep-sea exploration. Humans are not accustomed to being completely isolated in a small capsule. The lack of external stimuli, combined with the knowledge that failure is often fatal, creates tension that must be managed carefully. Even well-trained explorers experience moments of anxiety or discomfort. The absence of daylight disrupts circadian rhythms. The long, slow descent can feel endless. The unfamiliar environment outside the window, combined with the confined space inside, creates a unique mental strain. Researchers must prepare for this through training, but training cannot fully replicate the experience of being thousands of meters underwater. Another factor is decision-making under uncertainty. At extreme depths, conditions can change without warning. The terrain may shift, currents may appear, equipment may malfunction. If something goes wrong, options are limited. The crew cannot exit the vessel. They cannot repair the exterior. They cannot ascend rapidly without risking damage. They must analyse the situation carefully and act within strict constraints. This requires clear thinking and composure, but stress affects both. Humans are not machines. Our bodies respond to stress with physical symptoms: elevated heart rate, increased breathing, sweating, even in cold environments. These responses can complicate tasks that require precision. Physiologically, the human body also reacts to prolonged inactivity and pressure changes in subtle ways. Even though the pressure inside the submersible remains stable, the knowledge of external pressure can affect breathing patterns. Some explorers unconsciously hold their breath more often. Others breathe shallowly. This can lead to discomfort or dizziness. The confined environment restricts movement, which can cause stiffness, cramps, or numbness. These issues may not be dangerous by themselves, but they accumulate. The body is not designed for long periods of immobility in cramped conditions. Sleep becomes impossible during a dive, even if the mission lasts long enough that a break might seem helpful. The constant noise from equipment, the vibration of the vessel, and the need to remain alert make rest difficult. Fatigue affects cognitive performance, and the deeper the dive, the more important clear thinking becomes. Humans must rely on training and preparation, but even the best training cannot change physiology. The long ascent presents its own challenges. After hours of operating in a confined environment, the crew must endure another slow climb to the surface. While pressure inside the vessel remains constant, the knowledge that the vehicle must rise through kilometers of water creates an ongoing awareness of risk. If anything goes wrong during ascent, rescue becomes nearly impossible. The crew must remain attentive even when tired. They must monitor systems continuously, adjusting instruments as needed. Another human limitation is adaptability. Deep-sea organisms have bodies designed for cold, darkness, and pressure. Humans cannot adapt physiologically. Our bodies respond to extreme environments by shutting down or failing. Extreme cold causes hypothermia. Extreme pressure causes collapse. Extreme darkness disorients. Our senses evolved for sunlight, oxygen, and open space. We perceive the world through sight and sound, but these senses lose relevance in the deep. Machines can take measurements far beyond human ability, but humans cannot directly experience those conditions. We rely on readings and instruments to interpret the environment, but this creates a layer of detachment that makes navigation more difficult. Even if a submersible is engineered perfectly, human endurance remains a limiting factor. Missions must be planned around how long the crew can remain alert. Deep-sea dives cannot last indefinitely because humans cannot stay functional for long periods in such confined spaces. This restricts what can be accomplished. Machines might be able to operate for days, but humans can only supervise for hours. This gap limits the scope of human-led exploration. There is also the issue of emergency response. At extreme depths, if a problem occurs, escape is impossible. The crew cannot exit the vehicle. They cannot swim to safety. They cannot rely on rescue teams reaching them quickly. The only option is to ascend, and ascent takes time. During this time, any malfunction becomes critical. Humans depend on technology to survive the journey, and if that technology fails, there is no backup. This stark limitation influences how missions are planned. Safety margins must be generous. Risk tolerance must be low. These precautions reduce the number of potential missions and restrict the types of experiments that can be conducted. Environmental unpredictability contributes to human vulnerability. Even slight shifts in the seafloor can cause problems. A landslide triggered by tectonic activity might trap the submersible. A shift in currents might push it against a slope. These events are rare but possible. Human explorers must anticipate them, but predicting geological activity at extreme depths is difficult. This unpredictability, combined with human fragility, creates a narrow window of safe operation. Then there's the matter of long-term exposure. Humans cannot spend repeated long periods at depth without consequences. Even though pressure is controlled inside the vessel, the physical and mental strain accumulates. Fatigue from multiple dives affects reaction time. Stress affects sleep patterns. Constant transition between surface conditions and the deep-sea environment creates cognitive dissonance. Many deep-sea explorers report needing significant recovery time between missions. This reduces how often humans can participate directly in exploration. Another factor is sensory overload inside the submersible. Even though the environment outside is visually simple, the interior of the vehicle is filled with readings, screens, instruments, and data streams. Crew members must monitor depth, pressure, power levels, thrusters, lighting, camera feeds, sonar readings, and environmental conditions simultaneously. This requires continuous attention. Humans are prone to distraction, fatigue, and cognitive overload, especially in confined spaces. Mistakes can occur, and mistakes at depth can be disastrous. The impact of pressure on human psychology cannot be overstated. Humans evolved to live in an environment where danger is visible, audible, or at least perceptible. In the deep ocean, danger is invisible. The pressure outside cannot be seen or heard. Its presence is known only intellectually, yet the consequences of failure are immediate and severe. This creates a unique form of stress. Even calm, experienced explorers acknowledge that the awareness of external pressure lingers in the back of their mind throughout the dive. The brain responds to this environment with increased vigilance, which consumes mental energy. Isolation adds another layer. Communication with the surface is slow or limited. Real-time conversation may be delayed or distorted. This separation forces the crew to rely on their own judgment. Even when guidance is available from the surface, the crew must interpret and apply it with limited context. Humans rely on social cues for reassurance, but those cues become tenuous in the deep. This makes stress management more difficult. Human fragility becomes especially clear when compared to the organisms that live at depth. Deep-sea animals are not anxious about darkness. They do not worry about pressure. Their metabolism works slowly but efficiently. They have no need for large oxygen supplies. Their sensory systems evolved for this environment. Humans, on the other hand, require an artificial bubble of Earth-like conditions. We bring our own air, light, and temperature into an environment that provides none of them. If any part of that bubble fails, survival becomes impossible. All of these limitations demonstrate why human exploration of horizon deep is so difficult. Our physiology restricts how deep we can go, how long we can stay, and how effectively we can operate. Machines can extend our reach, but only within narrow boundaries. Even inside a protective vessel, humans remain fragile. The environment exerts pressure not only on the hull, but on the mind and body of anyone inside. As we move into the next part of this exploration, we'll shift from human limitations to the physical principles that shape the deep ocean itself, revealing how the interaction between physics and environment creates barriers that even the most ambitious missions struggle to cross. When the conversation turns from biology and human limitations to the physics that define the deep ocean, the environment becomes even more difficult to interpret. The conditions in the region surrounding Horizon Deep aren't mysterious because they disobey physical laws. They're mysterious because they apply familiar laws in ways that most people never experience. Everything that happens in these depths follows the principles of physics, but the scale, intensity, and combination of forces create results that challenge intuition. Understanding why exploration is so difficult involves understanding how these forces interact, not just individually, but as a constant system shaping every part of the environment. The first and most dominant force is pressure. Pressure is not simply a number. It influences every other physical property of the deep. It affects density, sound transmission, buoyancy, chemical reactions, and even the way materials deform. At extreme depths, water becomes so dense that its behavior shifts. The molecules remain liquid, but the compression alters how they interact with one another. They pack so closely that even small movements require more energy. This increased density affects how currents flow, how organisms move, and how sound travels. It also changes how machines operate because thrusters must push against water that behaves differently than it does near the surface. The second major force is temperature. Near Horizon Deep, the water temperature stabilizes just above freezing. This seems straightforward, but the combination of low temperature and high pressure changes how heat moves through the environment. Heat does not dissipate quickly. Thermal gradients become small. The cold water remains stable because sunlight doesn't reach it, and geological heat sources are limited. This stability slows biological processes and influences chemical reactions. Many reactions that happen readily in shallow waters become sluggish, or nearly halted at these depths. Enzymes in surface organisms depend on specific temperature ranges to function correctly. In the deep, low temperatures alter reaction rates significantly. Organisms living here evolved enzymes that operate efficiently in cold water, while machines must rely on heaters or insulation to maintain operational temperatures. Even the batteries inside a submersible lose power faster in cold conditions, adding another constraint. Another fundamental aspect of deep ocean physics involves buoyancy. Buoyancy depends on density. As water becomes denser under pressure, buoyancy changes. A vehicle designed for shallow waters may behave unpredictably in the deep. It might sink faster or slower than expected. Its response to thrusters may lag. Its stability might shift as pressure compresses materials slightly. Engineers compensate for this by designing ballast systems that adjust buoyancy along the descent. These systems rely on careful calculations, but calculations cannot predict every variable. The density of seawater varies slightly with salinity, temperature, and depth. Even small variations influence buoyancy. This means that a vehicle may need to adjust continuously to maintain stability. Sound behaves differently as well. In the deep ocean, sound travels faster because pressure increases the elasticity and density of water. But the path sound takes becomes unpredictable. Temperature layers, pressure gradients, and salinity differences create channels where sound bends or refracts. These channels can trap sound waves, allowing them to travel long distances before dissipating. This behavior helps some deep-sea organisms communicate or detect distant objects, but it complicates human exploration. Sonar systems rely on sound waves bouncing off surfaces, but refraction can distort the readings. A rock formation might appear closer or farther than it really is. A slope might seem gradual when it is steep. Mapping a trench without accurate visual cues becomes challenging, especially when sonar must compensate for the absence of light. The physics of visibility is another important factor. Light diminishes rapidly in water because water absorbs and scatters photons. The deeper a vehicle goes, the more scattering occurs, and the less useful artificial lights become. Even powerful lamps illuminate only a small cone. Particles in the water scatter light, creating a kind of underwater fog. This scattering increases with depth because pressure compresses water molecules, reducing the space through which photons can pass. As a result, even the best lights cannot reveal large areas. Visibility remains limited, narrowing the range of exploration. This constraint affects navigation, observation, and safety. Chemical properties of seawater also shift under extreme pressure. Gas solubility increases, meaning water can dissolve more carbon dioxide, oxygen, and other gases at depth. But the higher solubility does not make these gases readily available to organisms. The cold temperature slows diffusion. Some deep-sea environments experience pockets of water with extremely low oxygen levels. Organisms in these areas must adapt to survive with limited oxygen. Machines must bring their own supply, relying on sealed systems that maintain internal atmospheric pressure. Pressure also influences phase transitions of materials. At the surface, substances like methane hydrates remain stable only under specific conditions. In the deep ocean, high pressure stabilizes these compounds. Methane trapped in ice-like structures forms deposits along trench walls and the sea floor. These deposits remain solid under the current conditions but could destabilize if disturbed, releasing methane into the water. This creates a potential hazard for exploration. Even small disturbances can trigger shifts in these deposits, affecting local chemistry. Another physical factor is viscosity. While the viscosity of water changes only slightly under pressure, the behavior of fluids inside machines can change significantly. Hydraulic lubricants become more viscous, slowing the movement of mechanical parts. Engineers must select fluids that remain stable under pressure, but options are limited. Fluids that perform well at depth may underperform at the surface, and vice versa. This requires designing systems that can handle temperature and pressure changes during both descent and ascent. Density gradients create layers of water that do not mix readily. These layers form at different depths because temperature and salinity vary across the water column. The deep ocean contains layers that remain stable for long periods. When a submersible passes through these layers, it may encounter changes in buoyancy or experience shifts in stability. The transition between layers can cause minor turbulence or slight changes in movement. This turbulence is not strong enough to be dangerous, but it complicates precise navigation. A sudden change in density can cause the vehicle to rise or sink slightly, requiring adjustments from the pilot. The geology of the deep ocean also follows physical principles, but these principles operate under different conditions than on land. Tectonic plates interact along trench boundaries, creating subduction zones where one plate moves beneath another. These zones generate intense pressure and heat deep below the sea floor. Although the water in Horizon Deep remains cold, the rocks beneath experience significant stress. This stress can cause earthquakes, though most are too small to be felt by submersibles. However, even small geological movements can disturb sediment or change the shape of the seafloor. Sediment becomes compacted under pressure. Over time, it forms layers that tell a story of past geological events. Studying these layers helps researchers understand Earth's history, but the conditions required for this compaction make retrieving intact samples difficult. Fluid dynamics also behave uniquely at depth. Water movement is slow, but even small currents can influence the dispersion of nutrients or chemical signals. Because the water is denser, currents carry more force than they might appear to. A slight movement of water can push small organisms or particles considerable distances. Machines must account for this, especially when trying to maintain a stable position. Thrusters must counteract currents without disturbing sediment. Maintaining a steady hover requires continuous adjustments. Another physical limitation involves pressure hull design. Pressure hulls must resist deformation, but materials compress slightly under extreme pressure. Even titanium, one of the strongest and most pressure-resistant materials available, compresses under load. This compression may seem insignificant, but it affects internal volume. If the hull compresses even a fraction of a millimetre, the internal space changes. This can affect the pressure inside the vessel, the arrangement of instruments, or the fit of components. Engineers must account for these changes during the design process. The hull must not only withstand pressure, but maintain structural integrity across repeated compression cycles. The physics of ascent and descent create additional challenges. As a submersible descends, pressure increases gradually. The hull compresses, internal systems adjust. Upon ascent, the reverse occurs. The hull expands slightly. Air inside the vessel must remain stable. Any changes in temperature during ascent can cause condensation or affect pressure inside sealed compartments. As pressure decreases, gases inside equipment may expand, potentially damaging components. Engineers must build systems to manage this expansion. This process becomes more complicated if the descent includes long periods at depth, during which materials may have adjusted to extreme conditions. Another physical aspect often overlooked is the interaction between light and pressure at depth. When light enters water, the increased density causes refraction. At greater depths, the density increases further, altering how beams of artificial light spread. This affects how cameras capture images. Edges may appear distorted, objects may seem closer or farther than they are. Interpreting visual data requires understanding how refraction changes at depth. Without this knowledge, distances and shapes may be misinterpreted, affecting navigation decisions. The physics of sediment movement also create hazards. Sediment on the seafloor can be extremely fine, forming thick layers that accumulate over time. The high pressure compacts these layers, but they remain loose enough to be disturbed by movement. When a submersible approaches the seafloor, thrusters can stir up sediment, creating clouds that reduce visibility. These clouds take longer to settle in dense water, delaying exploration. They can also interfere with sensors, clog equipment, or obscure objects. In some cases, sediment may slide down slopes, creating small underwater avalanches that could damage a vehicle. Another physical challenge arises from the limited energy sources available at depth. Sunlight does not reach the deep ocean, so heat from the sun cannot warm the water. Chemical energy from hydrothermal vents is present only in specific areas. Most of Horizon Deep lacks these sources. Without heat, convection currents remain weak. The water stays cold and stable. This stability slows mixing and reduces nutrient distribution. Machines must carry their own power sources, as no renewable energy exists in this environment. Solar panels are useless. Wind cannot reach these depths. Wave motion does not translate into mechanical energy. This means machines rely entirely on batteries or power supplied through cables from the surface. Each method has limitations. Batteries restrict mission duration. Cables restrict movement. Pressure also affects how gases behave inside organisms and machines. Gases compress under pressure, reducing their volume. This is why swim bladders collapse in deep-sea fish from shallower waters. Machines must avoid trapped air because compressed air can increase pressure inside components or cause structural stress. Engineers eliminate air pockets by filling systems with oil or other incompressible fluids. This reduces the chance of damage but adds weight and complexity. Another area where physics plays a critical role is the behavior of salt. Salinity varies across the ocean, but at extreme depths, salinity can influence freezing point, density, and chemical activity. High salinity lowers the freezing point of water, allowing liquid water to remain stable at temperatures below 0 degrees Celsius. This affects the stability of ice-like substances such as methane hydrates. Machines operating near these deposits must avoid disturbing them, as abrupt changes in pressure or temperature could destabilize the structures. The physics of magnetism also come into play. The Earth's magnetic field behaves differently in deep trenches, especially near subduction zones. Magnetic anomalies can occur due to mineral composition in the rocks. These anomalies confuse compasses and navigation systems. A vehicle relying on magnetic guidance may veer off course. Engineers design vehicles to use multiple navigation systems to compensate, but unexpected anomalies still pose challenges. Fluid pressure inside organisms influences their buoyancy and internal structure. Deep-sea creatures often fill their tissues with incompressible fluids that maintain shape under pressure. Machines must replicate this with engineered solutions. Oil-filled housings protect electronics by equalizing pressure. But oil behaves differently under temperature changes. It may expand or contract, affecting pressure inside the housing. Balancing these forces requires careful engineering. Even simple mechanical operations become complicated under pressure. Hinges, joints, and seals must operate smoothly despite compression. Lubricants must remain stable. Moving parts must resist corrosion. Salt water corrodes metal rapidly. At depth, corrosion happens differently because oxygen levels are lower and chemical reactions slow. But over time, even small amounts of corrosion can weaken components. Engineers must choose materials that resist corrosion while maintaining strength and flexibility. Titanium, stainless steel, and specialized alloys become essential, but each material comes with trade-offs. The physics governing chemical reactions changes under pressure as well. Reaction rates slow. Diffusion slows. Electrical conductivity shifts. Even pH levels can fluctuate under extreme conditions. These changes affect sensors that measure chemical properties of the water. Sensors must be calibrated for depth-specific conditions, not surface conditions. Without accurate measurements, data becomes unreliable. All of these factors converge to create an environment where exploration requires not only sophisticated technology, but a detailed understanding of the physical principles shaping the deep. Pressure alone presents immense challenges, but combined with temperature, density, salinity, light loss, and geology, the environment becomes a complex system that pushes against every form of exploration. As we continue into the next part, the focus will shift from the physics shaping horizon deep to the larger boundaries that exist between what we want to explore and what is realistically possible, revealing why some limits are not just technological, but fundamentally tied to the nature of the ocean itself. When the limitations of physics, biology, and technology are all placed alongside one another, a clearer picture begins to form about why certain places on Earth remain so difficult for humans to explore. Horizon deep, like the rest of the ocean's most extreme environments, presents boundaries that do not yield simply because we have a strong desire to reach them. These boundaries come from the fundamental characteristics of the environment itself. They are not challenges that can be overcome by trying harder or building bigger machines. They exist because the deep ocean is shaped by forces that are incompatible with the conditions required for human presence. Understanding this helps explain why progress in deep-sea exploration remains slow and why complete access remains unlikely. One of these boundaries involves the scale of the environment. The ocean covers more than 2/3 of the Earth's surface. Its average depth is around 4 kilometers. Horizon deep is more than twice that. When we think about exploring a cave, a mountain, or a forest, we imagine a focused effort in a defined area. But the deep ocean operates on a scale that exceeds anything on land. It covers vast distances, contains complex terrain, and has physical conditions that remain stable over long periods. This scale means that even small advances require significant time, resources, and technology. Mapping even a small area is slow. Each dive can examine only a tiny portion of the environment. The boundary created by scale is not simply about distance, but about how many variables must be managed to explore even a fraction of the deep sea. Another boundary arises from accessibility. The surface of the ocean is dynamic. Waves, storms, currents, and weather conditions influence when and how exploration can begin. Launching a deep-sea submersible requires calm seas, stable conditions, and reliable support vessels. A single storm can delay a mission for days or weeks. Even slight surface conditions can affect deployment. This means that reaching horizon deep is not a constant possibility, but a narrow opportunity that depends on factors outside human control. Unlike space, where missions can launch within well-defined windows, deep-sea exploration is bound by the unpredictable nature of the ocean. Accessibility remains one of the most persistent obstacles. Time is another boundary. A deep-sea dive requires hours just to reach the bottom. The ascent takes just as long. The time spent at the deepest point is limited by power, air supply, and human endurance. This means that even with ideal conditions, exploration is brief. Machines can only stay at depth for as long as their power allows. Humans can only stay alert and functional for as long as their bodies permit. These constraints create natural boundaries around what can be observed. The ocean floor is vast, but exploration time is tightly limited. The mismatch between the scale of the environment and the time available to explore it means that knowledge accumulates slowly. Another boundary stems from unpredictability. The deep ocean is stable in some ways, but unpredictable in others. Geological activity can shift sediment, create small tremors, or reshape the sea floor. Chemical conditions can change. Currents can appear where none were predicted. Organisms can behave differently in the presence of lights and machines. Equipment can encounter unexpected obstacles. Even well-planned missions must adapt quickly to changing circumstances. Humans and machines are not well suited for environments where unpredictability can become hazardous. The deep ocean requires caution. Caution slows exploration. Slow exploration means boundaries persist. There's also the issue of cost. Deep-sea technology is expensive to build, maintain, and operate. Pressure-resistant materials require specialized manufacturing. Submersibles must undergo rigorous testing and inspection. Support vessels must be equipped with advanced technology and staffed by trained crew members. Sensors, cameras, and instruments must withstand extreme conditions. Every component must be replaced or repaired regularly. Funding for deep-sea research competes with other priorities in science, engineering, and exploration. Because resources are limited, only a small number of missions can be conducted each year. This limits the pace of progress, creating a boundary driven not by physics but by economics. Another boundary comes from the limits of our senses. Humans rely heavily on vision. We interpret the world primarily through what we see. But in the deep ocean, vision becomes nearly useless. The darkness eliminates visual cues. Artificial light reveals only small areas. Sonar provides data, but interpreting sonar images requires experience and training. Even then, sonar cannot fully replace sight. It produces outlines, shapes, and approximations. Making sense of these requires patience and skill. Because our senses are not designed for this environment, we rely heavily on instruments. Instruments must be interpreted, and interpretation takes time. This sensory limitation creates a boundary that restricts how quickly and accurately humans can understand what they find. Another boundary comes from the nature of risk. Every deep-sea mission carries risk. Machines can fail. Communication can be disrupted. Navigation can become uncertain. Human occupants depend on technology functioning perfectly. Because mistakes can be fatal, missions cannot proceed aggressively. They must move slowly, make conservative decisions, and avoid unnecessary risks. This reduces the amount of progress possible on each dive. When risk is high, exploration must be cautious. Caution creates limits. A related boundary comes from the fragility of the environment. While the deep ocean appears rugged, many of its ecosystems are delicate. Organisms living here grow slowly. They reproduce infrequently. They depend on stable conditions. A disturbance caused by a vehicle's thruster, a sample collection, or the presence of artificial light can disrupt local ecosystems. Researchers must balance the desire to gather information with the need to avoid harming the environment. Because of this, they often limit the number of samples collected, the amount of movement allowed, and the duration of exploration. Protecting the environment reduces the pace of exploration, creating another boundary. One boundary that often goes unrecognized is the boundary created by knowledge gaps. To explore effectively, we need maps, models, and predictions, but Horizon Deep remains largely uncharted. Without detailed maps, navigation becomes more challenging. Without understanding fluid dynamics at depth, predicting currents becomes difficult. Without a clear picture of geological activity, avoiding hazards becomes guesswork. These knowledge gaps slow progress because every mission must proceed cautiously. Filling these gaps requires exploration, but exploration proceeds slowly because the gaps exist. It becomes a circular limitation. Another boundary is technological maturity. Deep-sea exploration relies on systems that are constantly being refined. New materials, sensors, and propulsion systems are tested regularly. But technological development takes time. Manufacturing pressure-resistant components is complex. Testing must occur in controlled environments before deployment. Certification requires repeated trials. Each improvement comes with costs and delays. Until technology reaches a higher level of reliability, boundaries remain in place. Even the most advanced systems today carry limitations that will eventually be overcome, but not quickly. Human presence, while valuable for decision-making and observation, introduces another boundary. Machines can be built to withstand extreme pressure. Humans cannot. This means that any vehicle carrying people must include heavy, thick pressure hulls. These hulls limit speed, maneuverability, and endurance. A machine designed without humans inside can be smaller, lighter, and more flexible. But such machines cannot replace human judgment. They cannot adapt to unexpected situations with the same insight. They cannot make complex decisions without significant programming. Until autonomous systems become more capable, human presence will remain essential, and the limitations imposed by human fragility will continue to shape exploration. Another boundary comes from communication. Because radio waves cannot travel through water effectively, communication relies on sound or tethered cables. Both have limitations. Acoustic communication is slow. Messages can be distorted or delayed. Cables restrict movement and can become entangled. This lack of reliable communication creates a boundary that limits how far and how freely machines can travel. Without communication, machines must act carefully and conservatively. This reduces the area they can cover and the complexity of tasks they can perform. There are also boundaries created by the need to preserve safety margins. Engineers must design systems that remain safe even in worst-case scenarios. This means using thicker materials, heavier components, and redundant systems. These safety margins add weight, increase costs, and limit design options. Removing them would increase risk. Maintaining them slows progress. A critical boundary is the limit of energy. Batteries have improved, but energy storage remains a bottleneck. Deep-sea vehicles need power for propulsion, lights, instruments, cameras, communication, and heating systems. Each requirement drains energy. The more tasks a vehicle performs, the faster power drops. Because there are no external energy sources at depth, vehicles must return to the surface before power runs out. This limits mission length and reduces how much can be explored in a single dive. Even machines tethered to the surface via cables rely on power from the ship, but cables introduce drag and restrict movement. Energy limitations remain one of the most significant barriers. Another boundary is the limit of endurance for support vessels. Research ships face weather constraints, fuel limits, crew fatigue, and equipment maintenance. They cannot remain at sea indefinitely. They must return to port for resupply, repair, or crew rotation. These limitations restrict how many deep-sea missions can be conducted in a single expedition. Ships also require carefully timed schedules to avoid storms or rough seas. Even minor delays can reduce the number of dives possible. The structural boundary of the ocean floor itself also plays a role. Horizon deep lies at the bottom of a trench shaped by tectonic forces. The terrain is rugged and unstable in some areas. Slopes can be steep. Rock formations can protrude unexpectedly. Soft sediment can conceal hazards. Machines must avoid contact with the seafloor to prevent damage or entrapment. This reduces the ability to explore certain areas closely. The terrain acts as a physical boundary that limits movement. There are boundaries created by the limitations of measurement. Instruments can only detect certain wavelengths, chemicals, or physical features. Some phenomena remain invisible. Sensors may fail at depth. Cameras may capture incomplete images. Sonar may produce ambiguous readings. The limitations of measurement create boundaries around what we can understand. Without accurate measurements, theories remain incomplete. Without complete data, models remain uncertain. These gaps slow progress. Some boundaries come from safety regulations and ethical considerations. Deep-sea exploration must follow guidelines that protect the environment and ensure the safety of crew members. These regulations limit how often missions occur, what equipment can be used, and what procedures must be followed. While these boundaries are necessary, they also impose additional constraints on exploration. There are also logistical boundaries. Transporting submersibles, equipment, and crew requires coordination. Research expeditions must schedule multiple teams, including scientists, engineers, ship crew, and support staff. Equipment must be transported across oceans. Weather windows must be planned. The complexity of logistics slows progress and limits how often deep-sea exploration can take place. Psychological boundaries influence how humans approach exploration. The idea of descending into a dark, high-pressure, unfamiliar environment can create anxiety. Even trained researchers carry a sense of caution. This caution is appropriate but affects decision-making. Humans naturally avoid risk, especially when consequences are severe. This influences how missions are planned, how long they last, and what tasks are prioritized. Psychological boundaries are not limitations of skill or bravery, but natural responses to the environment. The combination of all these boundaries creates an environment where exploration remains partial and incremental. Some boundaries may eventually be overcome. New materials may improve pressure resistance. Better batteries may extend mission length. Advanced autonomous systems may navigate more effectively. But some boundaries cannot be eliminated entirely because they come from the fundamental nature of the ocean. Pressure will always be immense. Darkness will always be complete. Temperature will always be near freezing. Depth will always require long descents and ascents. These forces create limits that cannot be fully removed by technology. As we continue into the next part of this journey, the focus will shift to what can be observed from a distance. How observations made far above the trench shape our understanding, and why remote sensing provides insight even when direct exploration remains limited. When direct exploration is limited, as it is in the deepest areas of the ocean, much of our understanding comes from observations made far above the seafloor. This perspective might seem counterintuitive. We often assume that proximity leads to deeper insight. But with horizon deep and similar locations, closeness becomes a challenge. Distance, in many cases, becomes an advantage. Observing from above, whether from ships on the surface, satellites in orbit, or instruments suspended in the water column, provides information that would be impossible to gather from the seafloor alone. These observations form the foundation for everything we think we know about the deep ocean, even though they arrive indirectly. The most immediate observations come from research vessels positioned on the surface. These ships carry sonar systems, mapping equipment, and instruments designed to measure water properties. Multi-beam sonar systems send out sound waves that bounce off the seafloor and return to the ship. By measuring the time the waves take to return, scientists construct maps of the ocean floor. These maps reveal the shape of the trenches, the height of underwater mountains, and the contours of ridges. Even though the image they create is a representation, not a direct photograph, sonar maps remain one of the most effective ways to visualize areas too deep for continuous exploration. From this vantage point, scientists see Horizon Deep as part of a larger structure, the Mariana Trench. They see its curves, slopes, and connections to tectonic plate boundaries. They see where sediment accumulates. They see how the trench extends in multiple directions, forming a shape that is complex and uneven. Although the resolution is limited, sonar mapping helps identify areas worth further study. Without these maps, sending a submersible down would be like entering an unfamiliar cave without any sense of direction. But because the trench is so deep, even advanced sonar systems struggle to capture fine details. The sound waves must travel through large volumes of water, encountering temperature layers and density changes that distort their path. While the resulting maps are valuable, they leave many questions unanswered. Satellites positioned in orbit provide a different kind of information. They cannot see the seafloor directly, but they detect slight changes in sea surface height caused by variations in gravity. These variations correspond to features on the seafloor. A trench creates a small depression in the gravitational field, while a mountain creates a slight rise. By measuring these changes, satellites can estimate the shape of the ocean floor. This method offers broad coverage, allowing scientists to build global maps that capture features across entire ocean basins. However, satellite data lacks detail. It provides the general outline of trenches but not the fine contours. It reveals patterns but not specifics. Still, it guides research by identifying areas where detailed mapping would be beneficial. Another set of observations comes from instruments suspended in the water column. These instruments measure temperature, salinity, oxygen levels, and other chemical properties. Some drift with currents, others are anchored to the seafloor, some rise and fall autonomously. Together, they provide a vertical profile of the ocean. These profiles show how water properties change with depth. They reveal layers of water with distinct temperature or salinity. They show where oxygen becomes scarce or where nutrients accumulate. These data help scientists understand how water moves through the trench, how it mixes, and how it affects the chemical environment. From these observations, researchers see that Horizon Deep is not isolated. It interacts with the larger ocean. Water from surrounding regions flows into the trench, carrying nutrients, sediments, and organisms. Currents circulate slowly, influenced by the shape of the trench and the density of the water. These currents affect how sediment settles. They influence how organisms move. They shape the chemical environment. Even without descending to the bottom, scientists can infer these patterns from temperature salinity profiles and current measurements. This indirect knowledge provides a framework for understanding what happens at depth. One of the most informative remote observations comes from studying how sound travels through the ocean. Sound moves faster in deeper, colder water. By measuring sound transmission across large distances, scientists infer the structure of the water column. This method, known as acoustic tomography, reveals temperature changes and movement patterns. While it cannot provide imagery, it offers insights into how water circulates within the trench. Over long periods, this information helps build models that describe the deep ocean structure. Another important source of information comes from seismic studies. When earthquakes occur, they generate waves that travel through the Earth's crust and the ocean floor. Instruments on the seafloor and on land record these waves. By analysing how they move, scientists infer the structure of the tectonic plates beneath the trench. This helps explain how the trench formed and how it changes over time. Seismic studies reveal that Horizon Deep lies at the boundary between two plates, where one plate moves beneath the other. This downward movement creates the trench's depth and affects the geology around it. These observations from far above or far away provide context for the deep sea environment, even though they originate from outside it. Another method of observing the deep ocean comes from studying the biological material that drifts upward. Water samples from various depths contain DNA fragments, microorganisms, and organic particles. By analysing these samples, scientists infer what kinds of organisms live at depth. This approach, known as environmental DNA analysis, allows researchers to detect species that have never been seen directly. The DNA fragments floating upward carry clues about the organisms that reside far below. This method does not replace direct observation, but it expands what we know about biodiversity. Observations from autonomous vehicles also provide valuable insights. These vehicles do not carry humans but remain tethered to the surface or operate independently. They travel through the water column collecting data. Some reach deep depths, mapping areas that have never been visited by human-occupied submersibles. Although these vehicles still face the limitations imposed by pressure and darkness, they can cover more ground than human-led missions. They gather continuous data on water properties, currents, and acoustic signals. From this distance, they provide a broad view of patterns that would be difficult to see from a single location on the seafloor. Long-term observations also come from moored instruments that remain in place for months or years. These instruments record changes over time, seasonal shifts in temperature, variations in current strength, fluctuations in oxygen levels. These time series records provide a sense of how the environment evolves. They reveal patterns in how water moves, how nutrients circulate, and how external events influence the deep ocean. Without these long-term observations, understanding the deep would rely solely on brief snapshots from short expeditions. The moored instruments provide a continuous thread of data. Even though these methods offer valuable information, they carry limitations. Observations from far above cannot replace direct study. They cannot reveal the exact shape of individual rocks or the precise behavior of organisms. They cannot capture small-scale interactions. But they provide necessary context, guiding direct exploration and helping scientists understand what to expect when machines finally reach the seafloor. Remote observations also help identify where conditions change. For example, researchers may see slight temperature anomalies at certain depths. These anomalies hint at the presence of hydrothermal activity or unusual water flows. They may reveal areas where currents converge or diverge. These hints guide future missions. By knowing where unusual conditions occur, scientists can plan dives more effectively. Remote sensing also reveals how large-scale climate patterns influence the deep ocean. Although the deep remains cold and stable, surface conditions eventually affect it. Changes in surface temperature, salinity, or circulation patterns move downward slowly. Over decades, these changes reach the deep ocean, altering long-term stability. Satellites monitor the surface. Drifting buoys monitor mid-depths. Deep moorings monitor the bottom. Together, they show how global climate variations impact even the deepest parts of the ocean. Without these observations, scientists would struggle to understand how Horizon Deep fits into the larger Earth system. In some cases, remote observations offer clues about geological hazards. Seismic studies reveal plate movement. Satellite measurements detect subtle shifts in sea surface height. Together, they help identify areas where landslides or earthquakes might occur. These hazards can reshape the seafloor. They can disturb deep-sea ecosystems. They can influence sediment distribution. Observations from far above provide early warnings about these changes, even if they cannot prevent them. Another significant insight gained from remote observation is the recognition of slow processes that shape the deep ocean. While the seafloor appears static, it changes over long periods. Sediment accumulates gradually. Currents redistribute particles. Chemical gradients shift. These changes happen too slowly to detect during a brief dive. But by comparing long-term records, scientists see how these processes influence the environment. Understanding these slow changes helps interpret what submersibles observe when they finally reach the bottom. Remote observations also provide a broader context for biological activity. Drifting particles carry clues about organisms living at various depths. Microbial communities resemble those found near other deep environments. Organic material from the surface shows how nutrients move downward. These data help explain why certain organisms survive in horizon deep while others do not. They reveal patterns that direct observation alone cannot capture. Some of the most valuable information comes from comparing data across multiple locations. Observations from one trench inform understanding of another. Patterns found in the Pacific help interpret conditions in the Atlantic or Indian Ocean. Differences between trenches reveal how local conditions shape the deep. Without broad-scale observation, these comparisons would be impossible. Understanding what can be seen from far above also highlights the importance of indirect evidence. Because direct exploration remains limited, much of what we know about horizon deep comes from combining numerous types of data. Each method contributes a piece of the puzzle. Sonar maps reveal structure. Temperature profiles reveal currents. Seismic data reveal tectonics. Environmental DNA reveals biodiversity. Satellite measurements reveal large-scale patterns. Together, these observations build a coherent understanding, even without constant presence at the seafloor. Even though observations from far above cannot replace direct experience, they shape expectations and guide exploration. They help scientists decide where to send machines. They indicate where unusual conditions might exist. They identify areas that require closer examination. Remote observations form the backbone of deep-sea research, especially when direct access is limited. As we move deeper into this discussion, the next section will look at how human imagination fills the gaps left by incomplete knowledge, and how stories, legends, and speculation emerge when vast areas remain unexplored. Stories about the deep ocean have existed for as long as people have stood near coastlines and wondered what lay beyond the waves. Long before scientific instruments mapped the seafloor, and long before machines descended into the trenches, the human imagination filled the unknown with creatures and forces that explained what could not be observed. These stories reflected fear, curiosity, and respect. They weren't attempts to mislead. They were attempts to interpret an environment that offered no clarity. Even today, when technology reveals more about the deep than at any point in history, that imagination continues to influence how people think about the ocean. This becomes especially clear when talking about the regions surrounding Horizon Deep, where direct observation remains limited and gaps in knowledge persist. The ocean's vastness plays a role in why myths emerged in the first place. Large bodies of water challenge perception, they extend beyond the horizon, they hide what lies beneath. Humans rely heavily on sight to navigate and understand their environment, but the ocean conceals everything below its surface. This concealment creates space for imagination. When sailors in the past reported strange lights or shapes in the water, they weren't trying to create legends for entertainment. They were describing the unfamiliar using the concepts available to them. Without scientific explanations, the unknown naturally became mysterious. Even now, the deep ocean remains an environment where the unknown overwhelms the known. Horizon. Deep is one of the least explored regions on Earth. With limited data available, it's understandable that people speculate about what might exist there. But speculation is not the same as reality. Myths arise from the absence of information. Monsters arise from the attempt to fill that absence with something concrete. Understanding why these ideas persist requires looking at both the history of oceanic storytelling and the psychological need to explain environments that defy easy understanding. Historically, many cultures created stories about creatures that lived in the depths. These creatures often had exaggerated features, massive size, strange shapes, glowing eyes, or elongated limbs. These descriptions often came from genuine observations of real organisms brought to the surface. A decomposed whale carcass might look like a serpentine creature. A giant squid washed ashore might inspire tales of tentacled monsters capable of sinking ships. Bioluminescent organisms might be interpreted as supernatural lights. The deep ocean transformed these natural phenomena into narratives that made sense within the worldview of the time. The giant squid provides a clear example. For centuries, stories described enormous tentacled creatures capable of dragging sailors underwater. Without access to deep-sea exploration, these stories remained plausible. Only in the past couple of decades have scientists captured footage of giant squid in their natural habitat. The actual animals are large, but not the ship-destroying beasts of legend. However, the myth persisted for so long because the ocean seldom revealed the truth. The lack of direct evidence allowed imagination to fill the gaps. Even today, myths continue to emerge despite scientific progress. People sometimes speculate about unknown species living at extreme depths. They imagine organisms larger than any documented creature. They envision predators adapted to darkness, creatures with unusual sensory abilities, or forms of life not yet described by science. Some of these ideas stem from genuine curiosity. Others reflect the difficulty of reconciling the scale of the deep ocean with the limited amount of knowledge available. When an environment is mostly inaccessible, imagination expands to fill the void. Horizon. Deep's isolation amplifies this effect. Few machines have reached its floor. Those that have stayed only briefly. The footage captured reveals sparse sediment, slow-moving organisms and limited activity. But because the deep is so large and exploration so limited, it's natural for people to imagine what might exist beyond the narrow beam of a submersible's light. The darkness hides everything outside that small area. Even scientists acknowledge that unknown species likely exist in these depths, not because myths are real, but because biodiversity increases with exploration. Each new mission reveals organisms that were previously undocumented. This pattern reinforces the idea that the deep ocean still contains surprises. Imagination often centers on the idea of scale. The ocean contains some of the largest creatures on Earth. Whales, for example, reach lengths unmatched by land animals. The colossal squid approaches sizes that seemed unbelievable until specimens were found. Because of this, people assume that even larger creatures might exist at greater depths. But biological limits shape how large organisms can grow. Pressure, food availability, and metabolic constraints restrict maximum size. Living at extreme depths requires energy-efficient adaptations, and large sizes require substantial energy sources. Those conditions usually do not align in the deep. While unknown species may exist, creatures of mythical proportions are improbable. Another set of myths involves ancient or prehistoric creatures surviving in the deep. Stories occasionally suggest that dinosaurs or extinct marine reptiles might have retreated to the trenches. These ideas appear in popular culture but lack evidence. While some deep-sea species are ancient in evolutionary terms, they are adapted specifically to deep ocean conditions. Prehistoric marine reptiles required oxygen levels and temperatures that do not exist at extreme depths. Their physiology could not withstand the pressure. Evolution shapes species to thrive in their environment, and most prehistoric animals were not suited for the deep ocean. Still, these stories persist because the deep ocean creates an environment where confirmation is difficult. When people cannot see what exists, it becomes easy to imagine what might. The human brain looks for patterns, narratives, and explanations. When information is limited, those narratives become flexible. Myths flourish in environments that resist direct observation. The deep ocean, especially its deepest trenches, fits this pattern perfectly. Another reason myths arise involves the presence of bioluminescence. When lights appear unexpectedly in dark water, they evoke curiosity and speculation. Divers in shallow waters often witness bioluminescent plankton. In deeper waters, larger organisms produce flashes, glows, or patterns. These lights serve biological purposes: communication, camouflage, luring prey. But to observers unfamiliar with them, they can appear mysterious. Stories of glowing creatures, ghost-like forms, or deep-sea lights might have originated from these natural phenomena. Without a scientific framework, the displays become supernatural. Sound also contributes to myths. The ocean carries sound well, and unusual noises recorded by hydrophones sometimes generate speculation. Rumbling, clicking, or distant roars might be caused by seismic activity, ice movements, or marine animals. But when recordings lack clear context, interpretations become imaginative. Some unexplained sounds eventually receive scientific explanations. Others remain ambiguous due to limited data. These unresolved cases naturally attract theories that stretch beyond what is known. Another important aspect of deep-sea myths is the human relationship with fear. The deep ocean challenges survival. It contains pressure that can crush metal, darkness that eliminates vision, and cold that slows biological processes. Even though these features do not imply danger in the sense of hostile creatures, they create an environment that feels inherently threatening. When humans feel vulnerable, they often project that vulnerability onto the environment. Stories of monsters become symbolic expressions of fear rather than literal descriptions. They represent the danger of the unknown, not actual organisms. Some myths originate from misunderstandings of scientific findings. When researchers announce the discovery of new species or unusual organisms, simplified media reports sometimes exaggerate these details. A deep-sea fish with large teeth becomes a fearsome predator in headlines. A jellyfish with long tentacles becomes a monstrous creature. Sensational descriptions attract attention, but distort reality. Over time, these distortions contribute to myths. The persistence of deep-sea myths has both challenges and benefits. On the challenging side, exaggerated expectations can create misconceptions about deep ocean ecosystems. People might imagine that the deep is filled with dramatic or dangerous creatures, when in reality it is a quiet, slow-moving environment, with organisms adapted for low-energy lifestyles. Misconceptions can distract from genuine scientific insights. On the beneficial side, myths capture attention. They inspire curiosity. They draw people into the subject. Curiosity leads to questions, and questions lead to research. In this way, myths contribute indirectly to scientific exploration by motivating interest. Another important factor in understanding myths is the role of cultural storytelling. Different cultures have different interpretations of the deep. Some imagine benevolent creatures, others imagine dangerous ones. The stories often reflect cultural values, fears, or relationships with the sea. Exploring these cultural interpretations provides insight into how humans historically understood oceans long before scientific tools existed. The myths themselves become a record of human responses to the unknown. Even though modern science provides clearer explanations, myths remain part of human thinking, because imagination does not disappear when knowledge increases. Instead, imagination adapts. It shifts toward new questions. What organisms remain undiscovered? What geological processes shape the trench? What technologies will allow deeper exploration? These questions are grounded in reality, but they still reflect the same curiosity that created myths in the past. Modern imagination blends with scientific discovery in another way. Researchers sometimes find organisms that seem unusual even by deep-sea standards. Transparent fish, elongated crustaceans, gelatinous creatures, and unfamiliar shapes often challenge assumptions. These findings show that reality in the deep can appear strange without requiring mythical explanations. The deep ocean reveals that Earth contains more diversity than expected, and this diversity naturally fuels imagination. While these creatures do not match historic descriptions of monsters, they illustrate that unfamiliar life exists in places we seldom reach. Another interesting perspective is how scientific uncertainty contributes to imaginative speculation. When researchers acknowledge that they have only explored a small percentage of the deep ocean, some people interpret this as evidence of hidden creatures. But scientific uncertainty is not evidence of extraordinary organisms. It is simply an acknowledgement of the limits of exploration. The deep ocean contains unknowns, but unknowns do not guarantee dramatic discoveries. They guarantee that more research is needed. Understanding the difference between possibility and probability becomes important. It is possible that unknown species exist in horizon deep. It is improbable that they resemble the creatures described in myths. Scientists approach this with caution. They recognize that undiscovered species are likely small, adapted to low energy and cold temperatures, and similar to other organisms found at depth. The nature of the environment shapes what can survive. Imagination might explore alternatives, but biology and physics set boundaries. Another aspect worth considering is how myths change when new information emerges. When cameras first captured giant squid in their natural habitat, the myth shifted. It didn't disappear. It adapted. The creature was no longer a ship-destroying monster, but an impressive, rarely seen organism. People still find it fascinating, but the fascination comes from reality rather than fiction. This pattern might apply to other deep-sea species as exploration continues. As new discoveries occur, imagination refines itself. The deep ocean's relationship with myths also reflects how humans interpret silence. The ocean does not reveal its secrets easily. It does not offer immediate answers. The lack of information encourages speculation. When people cannot observe something directly, they rely on intuition, assumptions, or stories. This tendency is not unique to the ocean. It appears in every area where knowledge is limited: outer space, ancient history, and unexplored land. The deep ocean stands alongside these domains as a place where imagination thrives. Understanding myths does not diminish the real mysteries of horizon deep. The absence of mythical creatures does not make the environment less impressive. Instead, it reveals that the real world contains challenges and unknowns that rival those in stories. The deep ocean remains unexplored not because of monsters, but because physics creates limitations that technology struggles to overcome. The environment defies easy access, making it one of Earth's final frontiers. As the exploration continues, the stories humans create about the deep become part of the overall narrative. They show how people relate to unknown environments. They demonstrate curiosity and the desire to understand. They highlight how imagination fills gaps until knowledge becomes available. The myths themselves, while not literal, represent the human response to mystery. They have value as cultural reflections, even if they do not reflect biological reality. As the journey continues toward the next part of this discussion, the focus will turn to why some places remain unreachable, despite all efforts, and why certain limits, both technological and environmental, continue to define how deeply we can explore. When the long path through pressure, darkness, cold, technology, biology, and human limitation is traced all the way to its end, a difficult truth becomes clearer. Some places on Earth remain unreachable, not because we lack imagination or curiosity, and not because we haven't tried hard enough, but because the conditions themselves create limits that may never fully disappear. Horizon Deep is one of those places. The constraints that shape it are not temporary. They are woven into the structure of the planet itself. These are not barriers that yield to determination alone. They are boundaries maintained by physics, geology, and the nature of life. Understanding why some places remain beyond full human reach becomes a way of understanding the nature of exploration itself. The first reason some places stay unreachable is the combination of distance and pressure. Distance in the deep ocean is not measured in kilometers the way it is on land. It is measured in vertical descent, time, energy, and physical stress. The deeper the location, the longer the journey. The longer the journey, the more limited the time available for observation. Machines reach the bottom only after hours of travel. Humans inside submersibles operate under strict limits to avoid fatigue or equipment failure. Even if a perfect machine could descend quickly, pressure would still create risks. Every additional meter adds force to every surface. a small imperfection at shallow depth might go unnoticed. At the bottom of Horizon Deep, that same imperfection becomes catastrophic. The only way to avoid failure is to build equipment with extreme precision, but precision at this level is difficult to achieve repeatedly. This creates a practical boundary. Only a few machines can reach the deepest points reliably, and even those machines cannot remain there for long. Another reason these places remain unreachable involves the architecture of the trenches themselves. Horizon Deep is not a wide-open plain. It is a narrow, steep, irregular area shaped by tectonic forces. The walls angle inward. The floor contains ridges, depressions, and unstable sediment. Navigating these features requires precise control. Even small submersibles risk becoming trapped or damaged. Autonomous vehicles can map parts of the terrain, but they lack the intuition needed to maneuver through unpredictable environments at extreme depth. Tethered vehicles face the challenge of cable drag and entanglement. Free-swimming vehicles risk losing communication entirely. The terrain creates natural barriers that cannot be smoothed or altered. They are part of the landscape itself. The remoteness of these areas adds another limit. Horizon Deep lies far from major coastlines. To reach it, research vessels must travel significant distances, carrying specialized equipment and trained personnel. Weather patterns in the Pacific can disrupt schedules. Maintenance requires careful planning. Repairs must be done at sea or in specialized ports. Even if a machine breaks at depth, retrieving it becomes a challenge. If it becomes trapped or malfunctioning, it may never return. This remoteness increases costs and reduces the number of missions that can be undertaken. Fewer missions means slower progress, leaving large gaps in knowledge. Energy limitations also contribute to the inaccessibility. Deep-sea vehicles require power for lighting, thrusters, sensors, cameras, communication systems, and life support if humans are aboard. Batteries have improved, but even the best batteries run out quickly under these demands. A vehicle might spend 10 hours travelling to and from the bottom, but only 30 minutes on the sea floor. Increasing battery capacity adds weight, which affects buoyancy and increases pressure on the hull. Tethered power remains an option for some missions, but cables restrict movement and introduce potential points of failure. Without long-lasting, lightweight power sources, vehicles remain unable to explore large areas in a single dive. Communication challenges create another permanent boundary. As long as water absorbs and distorts radio waves, long-range wireless communication at depth will remain impossible. Sound works but carries delays and distortions. This limits the range of autonomous vehicles and the responsiveness of remotely operated ones. Communication tethers solve some issues but introduce others. These constraints mean that machines cannot venture far beyond certain distances without losing contact. The unreachable areas often lie just beyond these limits, where machines might physically travel but cannot communicate safely. Temperature and chemical conditions add further complications. Near freezing water slows chemical reactions and affects how materials behave. Lubricants thicken. Batteries lose efficiency. Biological samples degrade differently. Sensors must be calibrated for these specific conditions. The combination of cold and pressure creates an environment where even minor mechanical issues can force a mission to end early. Maintaining consistent performance in such conditions requires equipment that must be redesigned for every mission, making widespread exploration impractical. Another reason some places remain unreachable is the slow pace of scientific progress under these constraints. Each mission to extreme depths requires extensive planning, funding, and specialized teams. The time between missions may span months or years. Technological improvements occur gradually. Every new advancement must be tested thoroughly before it can be deployed at depth. Even successful equipment may not be mass-produced because the cost is too high and the number of missions too low. This slow cycle of progress contrasts sharply with environments on land or in shallow water where frequent testing accelerates development. In the deep ocean, progress remains incremental. There is also the issue of incomplete mapping. While sonar and satellite measurements provide broad outlines, they lack detail at depth. The seafloor around Horizon Deep includes features too small or irregular to detect from the surface. Without detailed maps, planning precise dives becomes difficult. A submersible may encounter unexpected slopes or obstacles. Autonomous vehicles may misinterpret sonar data. The lack of detailed mapping acts as a boundary, because exploration requires accuracy. Without clear navigation references, machines must move cautiously, reducing the area they can safely cover. Biological and chemical unknowns also limit access. Some areas may contain organisms sensitive to disturbance. Others may host chemical gradients that disrupt sensors. Unknown hazards such as methane hydrate deposits or weak sediment layers increase the risk of vehicle failure. These hazards cannot be predicted fully from afar. Until they are understood, some regions remain off-limits or require conservative operation. Geological activity creates yet another boundary. The tectonic forces that form the trench continue to act beneath it. Small earthquakes and shifts can occur without warning. Sediment can slide, rocks can shift. These movements create risks for vehicles. While the likelihood of large-scale events during a single dive is low, the risk remains real enough to impact planning. No machine can anchor itself safely in these environments, and no human-occupied vehicle can rely solely on sensors to predict geological changes. This unpredictability contributes to the inaccessibility. A more fundamental boundary arises from the nature of the environment itself. Some areas may be theoretically reachable with advanced technology, but not practically within reasonable cost or safety margins. Engineering a machine capable of withstanding extreme pressure is one challenge. Doing so at a scale large enough for extended exploration adds more challenges. Designing a system that can operate autonomously for long durations adds even more. When these challenges combine, the cost becomes prohibitive. Even if a machine could theoretically explore certain areas, building and maintaining such a system may never be practical. Another type of boundary comes from the limitations of maintenance and repair. When machines operate on land or in shallow water, malfunctions can be fixed quickly. Parts can be replaced. Diagnostics can be run. In the deep ocean, none of this is possible. If a sensor fails during a dive, the mission must adapt or end. If a thruster becomes damaged, the vehicle may not return. These risks limit how far machines can travel and how long they can stay at depth. They also limit the types of tasks that can be attempted. Without the ability to repair equipment at depth, exploration must remain conservative. Human safety creates boundaries as well. Vehicles carrying humans must adhere to strict standards. Pressure hulls must remain intact under extreme conditions. Life support systems must function continuously. Emergency procedures must be in place. These requirements limit the design of human-occupied vehicles. They make such vehicles heavier, slower, and less maneuverable. Because physically sending humans to certain areas carries high risk, many parts of the deep ocean remain too dangerous for human presence. This means exploration relies entirely on machines, which face their own limits. Another boundary involves the stability of the seafloor itself. Some areas may be too soft to support landing vehicles or instruments. Others may be too rugged for machines to approach. Unstable sediment can collapse under weight. Fine particles can clog equipment. Even carefully designed landing systems may not withstand sudden shifts. If the seafloor cannot support exploration equipment, the area remains unreachable. The environmental impact of deep exploration also creates a boundary. Human presence changes the environment, even subtly. Lights disturb organisms, thrusters stir sediment, sample collection removes material that may take years to replenish. Some regions are so fragile that even limited disturbance could cause long-lasting effects. For this reason, researchers often choose not to explore certain areas until they can do so responsibly. Conservation considerations become a boundary that prevents access until better methods are developed. There is also a more philosophical boundary. the limit of what we consider necessary to reach. Exploration is driven by curiosity, but not all environments offer practical value that justifies extreme risk or cost. As much as Horizon Deep fascinates scientists, there are questions that can be answered from indirect data or from shallower exploration. In some cases, resources may be directed toward areas where discoveries are more likely or more impactful. This does not diminish the importance of the deep ocean, but it recognizes that exploration must balance ambition with practicality. Another important boundary comes from uncertainty. Unknown factors create hesitation. If a vehicle enters an area where conditions differ sharply from surrounding regions, the risk increases. Sudden temperature changes, unusual chemical gradients, or unexpected currents can damage equipment or skew results. Without detailed knowledge, these uncertainties limit daring exploration. Scientists prioritize areas where data can be collected safely and reliably. Areas with too many unknowns remain out of reach until conditions can be predicted more accurately. As these boundaries accumulate, they create a landscape where some areas remain permanently difficult to reach. That does not mean they will never be explored, but the combination of physics, technology, logistics, and ethics ensures that exploration will remain limited. Even if breakthroughs occur in one area, such as improved batteries or stronger materials, other boundaries will still exist. The deep ocean is shaped by forces that operate on scales far beyond human control. These forces create environments that inherently resist complete access. Despite these limits, the existence of unreachable places does not diminish the value of exploration. On the contrary, it highlights why deep-sea research remains compelling. The boundaries remind us that the Earth contains environments that challenge understanding. They reveal how large the planet truly is and how small a portion of it humans have fully examined. They show that even with advanced technology, the natural world retains complexity beyond immediate reach. As the narrative moves forward, the idea of unreachable places becomes less discouraging and more reflective. It emphasizes that exploration is not just about reaching every location, but about learning from the attempt. Even partial access yields insights. Even limited missions contribute valuable data. The recognition that some places remain difficult to reach adds depth to scientific curiosity, encouraging careful observation, creative problem-solving, and appreciation for environments shaped by forces far older and stronger than human influence. And so the presence of unreachable regions becomes part of the broader understanding of Horizon Deep and the ocean itself. The limitations that define these areas are not barriers to discovery, but elements of the environment that shape how discovery unfolds. Exploration continues not because we expect to overcome every boundary, but because each mission, no matter how constrained, adds clarity to the picture of an environment that remains among the most challenging on Earth.